the concept of RAMS and PHMs. PHM in assets management applications basically. It is for the officials of Indian Railways and Metro Railways. Applications for these concepts in ensuring higher RAMs of railway assets will be elucidated through real-life examples. I am sure this webinar is also an introduction to an online certificate course on RAMS and PHM, which is planned to organize by Gautam Buddha University from September 2020 and December 2020. Subsequently, GBU planned to start 2-year MTech online course in RAMS and PHM from January 2021. Both the certificate course and MTech are mainly for working professionals in the field of railways, defense, metro, and railway-related companies. I am sure our university, in collaboration with you and with the cooperation from all experts, will make it a success and will add the values to the present knowledge, and our R&D status will really enhance. Thank you.
Thank you so much, sir. Now I'll give you a brief of what exactly we have done so far in our center. I'll just share you a presentation. As Sanjay sir has already told, the role of center at RAME in metro and high-speed trains is to impart courses and explore to develop essential parts of softwares in country with help of Indian academic and industrial collaboration. This is just one slide where in a snapshot I want to tell you what we have been doing so far. We had a roundtable industry academia meet in November 2018, a seminar on RAMS on 24th January 2019. We also held a workshop on RAMS on 22nd and 23rd April 2019. We provided internship to almost 100 students in 2019 on railways. And we also finally signed up an MOU with Noida Metro September 2019 and followed by a skill test for NMRC recruitment. This was a major breakthrough. This was our seminar, workshop, and we got a leverage of having students who can understand the railway nuances. This was the MOU which we signed in 2019 September. We were actually planning to start an MTech program, and we have already developed the code with the RDSO team and other metro and railway companies. Moving on, now I'd like to introduce Professor Kumar, who is the director of Luleå Railway Research, Luleå Technical University, Sweden. Professor Uday Kumar, sir, is the Chair Professor of Operations and Maintenance Engineering and Director of Luleå Railway Research Center at LTU. He's also a member of the Management Board, and he has more than 30 years of experience in research, consulting and finding solutions to industrial problems directly or indirectly related to reliability and engineering system. He has been responsible for several European Union on RAMS and maintenance technologies, PHM program for Chinese high-speed trains for CRRC, and Chinese State Shipping Corporation projects on intelligent maintenance. He was a member of Scientific Advisory Council of Millennium, Invest in Future program of Government of France 2014-2018. He is an elected member of the Royal British Academy of Engineering Sciences and was awarded the Nobel Science Foundation Award for significant contribution to science society and the recipient of Distinguished Alumnus Award of IIT BSc India, Lifetime Achievement Award for Society of Reliability and Safety, Recognition Award from Platform Council USA. Now I request Uday Kumar sir to kindly share his screen and give the presentation. Professor Amit Prakash sir, can you please switch off your videos? All the participants, please switch off their videos so that we can have a smooth flow of the presentation. Thank you so much, sir. Yes, Uday sir.
Yeah. Please. I'm still struggling to.
Sir, your screen is now available.
Yeah, my screen I'm not seeing. I have to see it also. I'm trying to see it. Because somebody should stop sharing, actually. Okay, let me see.
Yes, sir, it has come.
Okay, good. Good afternoon to my Indian colleagues and friends, and good morning to my colleagues in Europe and other parts of the world where it is before noon. What I'm going to do next 20 minutes, I'll be presenting what we are doing in field of RAMS and PHM. My focus will be mostly on new technology empowered PHM for railway system. A brief introduction to our center, Luleå Railway Research Center. What we are doing here, we are not focused on doing what we call basic research. Our focus is on advanced cutting edge applied research, which is multidisciplinary. And last year, we started also working on transdisciplinary research, where we much more focus on the societal issues and problem related to transport, and with a special focus on railway. Close cooperation with industry and society. 80% of our research programs are funded by industry or by some other government organizations like a Chinese government, Brazilian governments and all, and some have contacts with the African countries and all. Research for our motto is research for industry and society, not for library. So whatever work we do, it should be implemented within 4 to 5 years. And our programs are centered around training students to create jobs, not to seek jobs. So focus is on innovation. How can we convert our research results into product and services? So this is a brief our center. And Luleå University is about, it's in the north, and it's known for innovative research and education. We have 15,000 students in the campus, and we have 3 campuses, Luleå, PTO, Sollefteå, and 4th one is in Kiruna. We have aerospace research, and most of the launch for the Europe is done from the S range, where our aerospace research center is there. So this is a brief of where we are located. Here I will be focusing much more on the Luleå Railway research profile, what we are doing, and especially with reference to RAMS and PHM. And our center is almost 50 to 52 people are engaged, not very big, because it has to be funded by the industries. And we are the strategic center for maintenance and operation and maintenance of Swedish Rail Administration. So we get money from the government, some parts, and 80% of research is funded by either European research program, framework program, or by industry. So when we talk about research profile, so we have defined our research profile in 2 main research questions. One is estimation of remaining useful life. That's the holy grail of maintenance, or a reliability programs or a PHM program. We have been working for last 25 years on finding this component level and system level. We have a very good
Sir,
Sorry?
your presentation is stopped. Your presentation is stopped.
It's working now or no? I don't know. But here
Yes.
it's connected.
Yes, sir.
Yes, it's working.
It's working?
Yes, sir.
Yes, sir. Yes, sir.
Okay.
It is coming on a very small screen.
I don't know. I have a full screen here. That's the...
Somebody has started, Mr. Yadav has started presenting his screen in the middle. So Mr.
Yeah,
DK
yeah.
Yadav has started.
Actually, we should have a discipline here because it needs a digital presentation a lot more, because I'm seeing the full screen here.
Mr. Yadav,
can you once again go to full screen? Can you remove your stop presentation and then again start again, because the slides are very small.
Actually, are you seeing it now or not?
No. It is
So
very
then
small.
I should let me run it again.
No, we are able to see, but it is in a small screen. And the reason is that Mr. Jadhav, he just post his screen to share. So he should come out of the session.
Can someone request him that send a message to him so he should stop sharing?
Mr. Yadav, please don't share your screen. No participants to share their screen, please.
Actually, as an administrator, you should try to stop all the mics, videos, and you have a power actually. There's a button. You can close everyone.
Yeah, I think
Vidushi,
that
please.
you can solve the problem yourself. You can go to the smaller screen and go to fix the screen. You can mark this option and you will see the full screen.
So I'm seeing full screen here. Are you seeing my screen or not?
Well, we are able to see your screen, and that to full screen.
Okay, then let's start.
You have to pin it. Sir, you have to pin it. You have to go over there and pin it. There's a pin button. On that screen, you click. You have a pin button. You click on that pin button. You are able to see the full screen.
Okay,
I'm
yes,
seeing
yes.
Yeah, right. You are right, Vidushi.
Do I need
Yes,
to
sir,
do something?
please. No, nothing, sir. Please continue, sir.
So please continue.
Okay. Yeah. Please, actually, Vidushi, you can control all of the participants by some button is there. That you can stop everyone. Nobody should interfere, actually.
Okay, sir.
Okay. So what we are doing right now, our focus is on how to estimate the remaining useful life of system at asset level and system of system level, considering local and global risk scenario. That is a contextual information. What is remaining useful life? For some of the participants may not have fairly good idea. So I have a very simple schematic diagram of the remaining useful life. Let's say system is working from this point, you say expected performance. And with time, it may take any path of degradation. P1, P2, P3, and accepted limit is marked by this red line. So when it touches this point, this one, so and then you project that on the time scale, you get the expected, like X, how much, if I am the point of estimation, how long it is running. If it is a P1, X1, X2, X3. So you can model it. So you can calculate also the rate of loss of with time, how much remaining useful life you are losing. This is for a bearing, it's given like in terms of revolution and all. Second research question is health management part of the PHM. Appropriate maintenance decision and actions. Health management. What should I do when there is a problem? If I'm losing heavily my remaining useful life, why should I do it? When should I do it? Where should I do it? Lot more things like a prescriptive analytics. You do the prescription, what to be done. It should be generated. Now, to get this answer to all these two main questions, we have like a core research areas. And one area is a RAMS program, we run it. RAMS and LCC and risk analysis. We have written RAM for S because 2012, when European Commission was launching a shift to rail program, so we were contacted under the innovation program 3 for the track. So we introduced this, we said like RAMS should become RAM 4S. So we introduced 4S concept. And we are working on that. Earlier it was a RAMS, R-A-M-S, reliability, availability, maintainability, safety, security, supportability, and such. So these 4 were added. So we wrote this European. Since then, we are trying to work a lot more on this area because you all know security has become very critical now due to this digitalization, data-driven decisions, data sharing and all. Supportability becomes critical for infrastructure. Often it is not discussed in railway context because railway is a distributed linear assets. Like it's not in one place. So you need to decide where to put your supports, how much supports, how to reach to the logistics and all is taken care. And of course, sustainability is another issue, energy consumption, material consumption and all. So you put this RAM, how it will impact the sustainability goal of society, and thereby like energy consumptions, material consumptions, resource consumptions, and also security part. Then going back to other core areas, predictive maintenance. We were talking earlier condition-based maintenance, but when we start integrating context into the condition of a system, condition-based maintenance is only focused on the condition of the component or a system. But when you talk about predictive maintenance, so you're trying to integrate the context into your models and all. Or that becomes predictive maintenance. Then we have a e-maintenance, like utilizing the data, connectivity, cloud computing and all. And also asset management as a whole. And last 4 or 5 years, we are trying to introduce human factors, because human becomes the most critical item of all these processes. When you are going for automation, human becomes the very critical components, human error, or how can deal with this. So human machine interaction, rather we call it human machine interaction. So how machine to machine communication, what will be the role of the human, especially with respect to reliability, prognostics, diagnostics, operation and maintenance, etc. So this is our main core area. Then how we are using this concept into your design phase. Like you understand the function, you understand the application environment, do a RAMS analysis. Then you define the maintenance program, depending, because RAMS, reliability, quality, and maintenance are closely related to each other. When we measure the reliability, you don't measure how many items are working. You measure what is the failure rate. So loss of reliability, negative measurements. Similarly, in the quality, loss of quality. So loss of quality, loss of reliability is compensated through maintenance program. We cannot have the expected reliability. Then we bring the maintenance into the pictures, like a changing of components, doing maintenance after so many years. And that provides the basis for PHM and maintenance program, because RAM is an indicators we need to have, but PHM is a program that will give us assurance for reliability assurance or maintainability assurance or availability assurance. Then we can develop this cost-effective product. That's our research core. Then in operation, it's a typical psychology model or any model. What is the state of the system? Nowcasting. Why it is in that state? Diagnostics. What will happen in next 10 seconds or 10 hours or 1 hour? That's a prognostics. And how can we manage? That's a health management program. And then our research is much more focused on how can we manage the health in this part of this. Prognostic, what is the remaining useful life, etc. All the time focus. It's a railway we are talking. Safety, environment, sustainability, and return on investment. Because if there is no money, nobody will put money. If there is no return on investment, nobody will put money into that. So that's the key. Okay, now we'll be talking about RAMS and PHM in this webinar. Before we get into the RAMS, and we have also developed a framework for PHM, or a RAMS, what you call. We identified 4 distinct technologies, supportive technologies, that CMMS, sensors, all this technology you're using in train operations or like a locomotives and all. But that's everyone buys the same locomotives, but some people have a better availability, better capacity on the infrastructure. Why? Because different people are using different types of optimizing actions they are taking. And RAMS provides the foundation for optimization. So optimizing technology will lead to your predictive technology. That starts the PHM parts here. So RAMS, LCC analysis, condition-based maintenance, remaining useful life estimation. But since last 4 or 5 years, or 6 or 7 years, I will tell, much more focus is on developing transformative technology. Since railway has boarded the digital train, it has become much easier to introduce this new and emerging technology in railway to get the really expected capacity, design capacity, or design availability and all. That is like in transformative technology, digital twins, IoT, machine learning, and here is our main focus area now. If it is a successful, what is different between transformative and disruptive technology? When transformative technology becomes cheap, easy to use, and it becomes popular, it becomes disruptive, like a Uber became, Airbnb, etc. So this is the foundation. We'll disrupt the way railway is maintained. We'll disrupt the way railway is operated. That we are looking for continuously. And it's a continuous improvement process. Key foundation, railway is struggling to how can we converge the information silos with the operational silos. Operational technology are on the trains, like trains operated by SCADA, PLC. They have lived their own lives. Then we have information technology, type of customer waiting, how to integrate, where are the supports, how the signaling system, how many people are. So it has to converge both these two. IT must converge with operational technology to get this transformative technology and solutions for railway. And to foundation for everything is what we call this digital transformation, digitalization. Digitalization is the key. It's a foundation. So we have to go for digitalization. Then only we'll get this, what we call transformative and disruptive. But before we, like what does also like we wrote that it integrates an interaction between two different systems and facilitate correct decision making, digitalization, because you can see the what is happening, what are the in real time, you can see the risk on what type of risk by different decisions you are taking and all that will be facilitated by digitalization. Now next point was this railway domain knowledge. Domain knowledge is important. Whatever I do, why many programs have failed, you know, the GE had a big program called Predix. They tried to implement in railway, 3 countries. India was one of them 4 years ago. Why did it fail? One of the reasons was they didn't have the full knowledge of the domain. They developed the program without understanding how railway functions, how all this infrastructure, train operator, train management systems, how these things can be connected. And even more important, what are the regulations, local regulations? What are the customer requirements? All these things has to be integrated. So domain knowledge is the key. Anyway, this is our PHM program we are developing considering all these issues. We have about more than 40 projects running, 42 exactly on this area, connected directly and indirectly. And all these areas are starting at TRL level 3. I'm not going to explain what is TRL and all. It's like a start with the fundamental basic research starting the fundamental research, you develop new area and push the technology, but mostly governed by the market pull, what market want, what the contractual requirements. So start with the 2.5 actually our work and goes up to 7. Then we have another separate center that takes from here and convert into the product and services. That's our key, research and innovation. Like we have many many companies have been built on our concepts, and some of them has been listed as one of the hot company for futures. One of the 2 are like Prage OIB, e-maintenance 365 earlier, smart maintenance, performance in cold, etc. There are some companies based on the centers research and all. Our infrastructure, railway research corridor, we have 40 kilometers long live corridor. Trains are moving. It's not a dead corridor. It's a live corridor. Not a passive, it's active. And we do all our experiments there. We have a data center, we collect all the data. We have a condition-based maintenance lab where we develop the condition monitoring we are measuring. E-maintenance lab to provide servers and all. And last December, we started what we call AI factory for railway. All these labs will be brought under this umbrella, AI factory for railway. It's funded by the government, Swedish government, but all these projects will be brought finally on this platform. That's our goal. And we'll be developing solutions, concepts, roadmap for digitalization and all. So this is one area. Many companies are indicated into many. There are 14 partners, industrial, Alstom, Professor Darsin company. He is also connected to that indirectly on this one. This is our corridor, 40 kilometers corridor. There are many instrumentation, different places. RAMS side, we have been talking. What is difference between RAMS and PHM? RAMS gives you what is the performance, agreed, contractual. It provides a basis for contractual agreement is being fulfilled or not. It identifies the weakest link and gives you also guidance for the improvement. Whereas PHM is like MSAT detection, diagnostics, prognostics, etc., and identifying uncertainty, future uncertainty, and what type of models are needed. So this is a core of this too. Like in RAMS, you try to find the failure data, discrete failure rate, mean time to failure, but here focus is on finding remaining useful life, etc. In RAM, we talk about the population of components. In PHM, we are focused on assets. I would say the train will move from point A, station A to station B or not. And if it is not moving, what are the issues? How can it be made to move? What is the best solution to deal the situation? That is it's a Professor Darsin. I was discussing with him. So that he has been clarifying these issues with us. PHM, I will know, impose utilization. We have been talking what is doing, so I will not give time here. PHM, we have a 2 main data-driven model and physics-driven model. Data-driven model is more key, like what you are doing, maintenance analytics, big data analytics. But what you get from data-driven, it's like a black box solution. It doesn't include the physical models of how component fail. That's the key. So what we are trying to, we have worked a lot with the bearings in the train to developing hybrid model. So physical model and data-driven model combined, that gives us the hybrid model. We are also trying to introduce this symbolic model where case-based reasoning. We don't have solution. Both has a shortcomings. Data-driven model has its own shortcomings because it doesn't understand the physics, doesn't explain. It's based on the experience. Mostly you took the working proposition and get to the data-driven model. Physics model is based on the lab and all, but it has no information about the context information. So these two, then we introduce with the symbolic model, case-based reasoning and all, empirical understanding, that you can get a better rule understanding. That's our another focus. Big data, these 3 items, now people say 5 items, we don't get into that. This is the analytics we are doing. Okay, descriptive, what has happened and what is happening, both are important in a component. Predictive, what will happen, when it will happen. And then already I said, like a management, what should I do, why should I do, when should I do, how should I do, and to get the best possible maintenance decision and solutions. That's the role of PHM. Gives us the best possible roadmap, best possible guidance. It visualizes the risk, what risk I'm taking by taking these actions. That's the main focus here. So there are 2-3 issues here. Analytics gives us nowcasting. Where is the train? Which route is the available? Which on the station? There are many selections. What will happen? What has happened? Why? This is a nowcasting. That we did a big European project on this area into rail. You were leading that part. And forecasting, that everyone wants, remaining useful life, and health management. That's our lab actually, e-maintenance lab. Now it's merged with the AI data factory. Example, this is analytics based on the iron ore trains. And focus was on to find the flange depth of the, and this figure is taken from the one of our, what is called like a spin-off company from our group, Pre-Jobe. It was also listed as one of the 33 top company startup in the country, innovative company and all. And we do the, it's like, you see the next figure you'll see. This is the predicted current degradation rate, predicted degradation rate, and recommended by the manufacturers. So how can we find this one? Like dynamically, in real time, we can monitor every wagon or every train sets. And we can identify which wagon needs to be maintained when. So you can club different type of wagons and you can take it for maintenance to the nearest workshop and all. So this is the purpose of this analytics. Challenges, I have been talking, it's easy to look very sound, but there is a, data is the main challenge for PHM. Integration of context into rule models. Like this all explained like this. If train is moving, and if I'm 20 kilometers from the harbor, iron ore train I'm talking, shall I, if there is a bearing is showing the high temperature, shall I stop it or I reduce the speed from 90 kilometers, 80 kilometers to 40 kilometers, and I should take the train to the harbor, and their repair can be taken. So you have to understand the context. If I don't come in 3 hours, what are the penalty? If I run the train up to 3 hours and reach the harbor in 1 hour, what are the risks I'm putting? So this is a very interesting area. In fact, first time, actually, we presented a paper on this, context-driven condition-based maintenance. We didn't call that term rule. That was in 2010-11 in US. And then we started calling it context-driven rule estimation. So you integrate the requirement of customers into your rule model, into your PHM model. I think I will be nearing my time. I will be coming nearer also. Field data, not PHM. Purpose of designing PHM, it's not good. And time for degradation are very long, so it takes time. So these are challenges. Future directions, where it will, since the title is a new technology empowered, what will happen? It will greatly depend on the development in IT capabilities, IT security, how IT data can be dealt and all, and forces with respect to mobility and flexibility. 5G, everyone knows. It's almost knocking at the door many places. We have tested 5G in our bearing test one program like in a smart bearing on the in the railway. Due to this communication part, we could not get what we wanted to get. So 5G is already in place, and it will accelerate the implementation of PHM program, RAMS program, and new and what we call like a smart maintenance program. But what is 6G? What is different between 4G and 5G? 4G created a human community, society. Like I started using WhatsApp, you know how quickly we are using. 5G is a simple man, we call it like it will create a machine community now, machine to machine communication. Machine A will communicate with machine B, but human role will be only to watch it and see everything is done. Then what is 6G? Very few people know that. Last 3 years, 6G research is going on. And one of the leading countries, US, China, of course, is doing in Shenzhen. I was there last year visiting Shenzhen for different purposes. And Finland, the home country of Nokia, they have put 200 million euro on 6G research. And one of the purpose of 6G is to data, when you are sharing, data itself will become intelligent. It will not come to me. It will go to Mr. X or Mr. Y, depending on the need and the requirement. And also data will be optimized during the pipelines, and the data pipelines will be activated. So this is a key for the next 3-4 years, 6G. Of course, robotics automation, I will also power of big data, cloud computing, AI we have been talking, and development of machine community and use of social media. That's the, actually this slide I'm having for the last 10 years. I say to, in a 5 years, I told 10 years ago that machine will be using social media. Again, I'm telling 3 to 5 years, when 6G comes, machine will be twittering. I'm feeling bad. I have this type of overload. Everyone will tell, yes, due to the track problem or due to the change in climate or something like that. Is it not? And then may get a solution. And whether I should run on this speed or not. So this is going to be really future here. And it is there on the knocking on the door. We are testing it. It will work. I am 200% sure, not 100. Okay, this is one example of this is a smart bearing of SKF, I will tell it. It is on the trains. We have been testing. There was a self power harvesting. Everything is there. It was developed a lot of concept in our SKF center in Luleå. We have a condition monitoring center of SKF for developing a smart bearing, and it is being tested. Hopefully this bearing will not be monitoring its own health. So it will, bearing can be a component, bearing can be a system, but it can be also a sensor. So this bearing was developed here and is still under development. It will become a sensor for the train. It will measure the track condition, it will measure the vehicle condition, and it will measure its own health in different way. And it will be self-power sufficient, because in a goods train, power is a big issue. And hopefully it will be connected to our AI factory. Okay, concluding remarks. An effective PHM deals not only with the whole life cycle management and cost, but facilitates integration of new technology. What I've been talking is a new technology. So when this program should be self-evolving. You know, technology evolves like a living organism. Tomorrow, living after 10,000 years, it becomes different. Technology is also like that. Today it is like that. After 3 years, different technology will come. So our program should be designed to integrate things, and PHM has this probability. Like in PHM condition monitoring, we have started a big program on monitoring the materials health, like a track health at nano level. Because if crack comes, there is a changes in the atomic level, structural change. Can I monitor it? Answer is yes. But precursor and how it can be used, like using nano voltage and all, exactly the strain gauges. So technology and PHM are very closely related. An effective PHM visualizes risks and associated utility value associated with each alternative decisions based on informed risk. That's the key. I can see it. If I'm taking the train out for maintenance, now train is in service, what risk I'm putting into the business, what risk I'm putting into the capacity of the track, what risk I'm putting into the capacity of the fleet. You can see the risk with different alternatives, different actions. That's the PHM program with the technology. Thank you.
Thank you so much, sir. In fact, we are very delighted to have you today, and you've shared such a nice presentation with all our participants. I definitely feel all our participants are going to benefit out of it. Now I request Dr. Rajesh Mishra, sir, who is currently working with Gautam Buddha University, to give his presentation Let me introduce him. He received his PE Electronic Engineering, MTech Reliability Engineering from Reliability Center, IIT Kharagpur in the year 2000, 2005, 2009 respectively. He has research interest in the areas of reliability, railway processing and communication network. He has to his credit several research papers in international and national journals. Sir.
Good afternoon.
Sir,
Hello.
can you share your screen?
I am
Mr. Sir?
audible.
Yes, you are audible, and please share your screen, sir.
Okay. Respected sir and friends, it is my pleasure to talk about RAMS fundamentals. So I am presenting on the introduction to the RAMS.
Sir, put it on the full screen.
Just a minute.
All the other participants, can you please switch off your videos, because bandwidth will become a limitation then. Yes. Mr. Sir, yes, you are on the screen now.
Yes, it is there.
Yes, sir. Swami, Deepak Sharma ji, can you please switch off your videos? All the participants are requested to keep their videos switched off.
Hello.
Ishra sir, you can start your presentation. Screen is there.
My slides are visible or not?
Yes, your slides are visible to everybody.
Okay. Thank you, Vidushi, Dr. Vidushi. Respected sir and friends, it is my pleasure to talk about RAMS fundamentals. So before starting my presentation, I want to discuss my favorite terms, failures. So in daily life, each of us observe the bridge suddenly collapse, too much crowds in the road on the roads, plane crashes, railway accidents, floppy disk not working, computer not working. Everywhere we can see these type of happenings. So failures can result in significant economic losses and physical damages or threats to human life. So finally, conclusion is everything on this earth has a finite life. So impact of product and system failures varies from minor inconvenience and cost of significant losses including death of many persons. These failures includes the bad engineering design, faulty constructions, manufacturing process, human error, poor maintenance, and so many reasons are there for the failures. So conclusion is, everything on this earth has a finite life. We never get the 100% reliability of the systems. So failure, the definition of failures is a termination of ability of an item perform a required function within a previously specified limits. Of two types of failures are there, soft failures and permanent failures. Soft failures are the temporary failures and permanent failures are the hard failures. There are causes of the failures like a human error, acts of the nature, hardware failure, software failure, and so on. So according to the failures classifications, we can categorize in the failures in the two types. One is the failures of the catastrophic failures. These are the completely failures, or we can say these are the sudden failures. Whereas the degradation or wear out failures are the gradually failures, and these failures are partially failures. So the question arises, why product fails? Then what to learn from these failures? When accident happens, what are the factors that can drive the unlearning process? How can organization learn and change their policies, routines, and procedures through feedback of these failures? So single terms behind the failures is a stress. So when stress is more than strength, the system will fail, and when the strength is more than stress, the system will success. There are various types of failures and their reasons behind, like a poor design. The poor designs may be from the materials, wrong materials uses, wrong dimensions, tolerance, and so on. Similarly, various reasons failures like incorrect manufacturing, improper testing, complexity, improper maintenance, raw material supply, and quality assurance, packaging, shipping, transportation, improper installation, and operational instructions, and human errors also. So these are the various failure reasons and their details. So beginning of the reliability era, the concept of reliability developed slowly until World War II. During this World War, the 50% of defense equipments were found to be a failed state. The major role of the failure is the vacuum tube failures. So first time reliability was born as a branch of engineering in USA in 1950s. So system reliability generally we can classify it in two categorization. One is the software reliability, second one is the hardware reliability. So the software reliability are generally the departure of the programs or operation from user requirements, whereas hardware reliability are the termination of ability of an item to perform a required functions within a previously specified limits. So generally the whole systems like a medical science, civil, electronics, mechanical, any science background subjects or a engineering background systems, both are dependent on the hardware reliability or a software reliability. So there are various failures and reasons. So all the failures according to the reliability, we classified these reliability by the bathtub curve or a life characteristics curve. These curves are the benchmark curve for the failures. This bathtub curve we can classify it in three phases. One is the infant mortality part, where the failures are very much, whereas the second phase goes to the useful life failures. These are the continuous nature of the systems, and final phase is the wear out failures, means the system will degradedly and finally it goes to the failures. So as I discussed, the software reliability and hardware reliability, the main difference between the hardware and software reliabilities is the phase of the wear out phase, where there is a, in software reliability, there are continuous degradation is not possible. The software is upgraded time to time. So software reliability are generally the hypothetical type of work where the wear out conditions cannot, nobody can see and nobody can measure the wear out of these type of failures. So first, the term performability came from the Professor KB Mishra to improve the system reliability. The performability depend on the dependability and sustainability, where the sustainability are generally related to the environmental conditions and time, whereas the dependability are again classified in survivability of the systems and safety of the systems. The RAMS concepts came for survivability, the quality, maintainability, RAMS, security, availability, risk, and so other categorizations are in the survivability portions. Professor K.S. Trivedi simultaneously gives a dependability concept. The dependability concepts classified in the attributes, means, and threats. So that is also the important part for the reliability measures and evaluations. Now we came for the definitions of the reliability. What is the reliability and what is the availability and what is the maintainability and what is the safety? So in two senses, we can define the reliability in a general term, the ability of a system to perform a required function under given condition for a given time interval. The precisest definition of the reliability can say the probability that a system will operate without failure under given conditions for a given time interval. Whereas the availability, a small difference in reliability and availability. Availability means a particular time the system should be available. So in general way, the ability of a systems to be in a state of perform a required functions under given conditions at a given instant of time or at a given time interval, assuming that the required resources are provided. Similarly, the maintainability can be defined as the ability of the systems under given conditions of use to be retained in or restored in a state in which it performs a required functions when maintenance is performed under given conditions and uses stated procedures and resources. The precise definition of safety is it is an event like to result in a death or injury of the persons. So significant material damage or other unacceptable consequences are just safety. So my next slides represents what are the use of the reliability in the information and communication technology and railway industries. There are various companies works on the reliability in the ICT field like a Verizon, Cisco, AT&T, Huggies, and Emerson, and so on. Similarly, where the Alstom, Siemens, Bombardier, and every railway company requires the reliability nowadays. The first question arises, how we can evaluate or measure the reliability? So there are so many statistical methods we can use for the reliability evaluations and measures. So these statistical measures generally require the data sources. So data sources we can get from the internet or a live data. Similarly, there are various software tools for reliability analysis. Various companies product developed for the software tools developed by the reliability analysis. Actually, the RAMS is not a new word. In 1812, the Bayesian probability started by the mathematical models. Then simultaneously, similarly, the uses of the mathematics and so on. There are so Petri nets and so many fuzzy logics, and we can use the various type of mathematics for the reliability evaluations. So these are the three terms: MTTF, MTBF, and MTTR. These are the matrices for the reliability evaluations. So time between two failures is generally is the time to repair and time to failure combination of the systems. So reliability terminology, generally we find or measure the system reliability or by the part reliability or a subsystem reliability by using the time to failure and time between failure and time to repair and time to repairs. Now, I want to discuss for the railways or high-speed trains for the reliability uses. So we want to explore the research and development in the era of ICT and with the RAMS concept for a futuristic rail for Indian. We want to develop new methods, knowledge, and insight into the engineering of safety critical system and cyber security in context of the railways. We want to develop essential parts and software in our country through academic industrial state. So that was our primary objective to start in Gautam Buddha University Center, how we can develop these softwares and hardwares in India. How we can go for the, we are capable for getting these softwares and hardwares here in India. There are in the second one is so many challenges are the ICT field also. So railway operations are becoming increasingly automated and integrated. So advanced signaling, asset management, improved the video security, put tremendous pressure on the existing network. So network reliability, I think, is also important part for the railway. And passengers are demanding to be connected, entertained, and informed during journeys. So it is also required. As the railway operators, it is difficult to deal with this complexity while improving the capacity, maintaining punctuality, and increasing safety. So all while reducing cost and carbon footprints, we want to ensure on time, safe, and connected journeys. The solution is the dynamic communication for the railways. So in dynamic communication for the railways, there are the operations part, there will be a safety and security part, and there will be the passenger experiences. So by time to time, we can collect the data from the passenger experiences and existing operation schemes. We can develop the software and hardware for futuristic and high-speed trains in India also. So this is my small presentation. Thank you very much.
Thank you very much, sir. Rajesh Mishra sir has already told us about the small aspects of RAMS. What? Professor S.K. Chaturvedi sir, who is the head of Subir Chaudhary School of Quality and Reliability, IIT Kharagpur. Now he'll be presenting his presentation, and let me introduce him first. Professor Chaturvedi is currently working as professor and head at IIT Kharagpur, and he has various publications. The links will be shared to you. You can visit the publications list. He has published his research work in most of the international journals of his research interests and executed several consultancy projects of private and government organizations. He is also on the review panel of IEEE Transactions on Reliability, IEEE, IJQRM, IJ International Journal of System Science, International Journal of Failure Analysis. He has authored 2 books and contributed chapters edited by leading authors in the area of reliability. He is also a senior to IEEE Executive Committee member, BIA Sectional Committee member, Reliability of Electronics and Electrical Components and Equipment. He is on the editorial board of International Journal of Mathematical Engineering and Management Sciences and has been a co-editor-in-chief to IJPE as well. Thank you very much, sir, for being over here, and I request all the participants, they will thoroughly enjoy your presentations.
Thank you, Dr. Vidushi. Let me share my screen first. Can you see my screen?
So your screen is visible now? You can put it on the slide. Yes, it is visible. You can put it on the slide.
Is it visible?
Yes, sir.
Thank you. So very good afternoon. Possibly many of the participants or the speakers might be in sleepy mode, but it's okay. Sometimes we have to take a call on such occasions. Thank you very much, Gautam Buddha University, for giving us this opportunity to present the webinar based on that. I am Dr. Sanjay, representing Subir Chaudhary Schools of Quality and Reliability, and my presentation is in 2 parts, in fact. First is system effectiveness and reliability engineering, how they are related with, and another is based on generally people face how to specify reliability, how to measure reliability, something like that for a given system or so. So this presentation based on this and the MTBF, which is commonly treated as a metric for reliability specification. So I'll begin my presentation, and about my school. Briefly, I'll say that we are dealing with we are concerned with the research and education in the area of reliability and quality engineering, and basically we deal at the level of MTech and research level, that is PhD. And you can get more details on our school. This is the web address from where you can get it. So without wasting time, I come to the first part of my presentation, system effectiveness and reliability engineering. So what is system effectiveness? The question arises. Is it anywhere related to the RAMS? So if you see from the historical point of view, you will see that system effectiveness had its beginning in the very early 60s. And you can say that after post-World War II, there are 2 branches came up in a very rigorous way. One was the operation research, because this branch was related to the optimal resource utilization. Another was when the system is demanded to or the use, it was failing. So another area which cropped up was reliability engineering. So system effectiveness comes in early 60s, and major efforts was directed by 2 agencies. One was a effective industry advisory committee, WCAC. Another was ARINC, Aeronautical Radio Incorporation. The first agency, the first advisory committee presented 6 reports in 11 volumes. Possibly some of the reports might be available on internet, which involved in the totality of the requirement associated with the system's capability, which is a qualitative term, availability, supportability, dependability, as well as reliability. If you see, the reliability is one of the component of availability and supportability. And if you nowadays you will see the dependability term is taken up. So dependability this reliability is also one of the component of dependability, and Dr. Rajesh has shown you one figure, performability engineering, where this reliability is again become a major component. Another component, definitely you will see the maintainability part, which overall gives you the availability part. So they published another contribution made by the ARINC, which was established in 1929 and providing a solution provided to several industries, right from aviation to the healthcare industry, transportation and communication industry, defense industry, government, several other government agencies. And they have given to place the importance of reliability, engineering in the overall picture and in the concept of system effectiveness, which encompassing reliability, maintainability, dependability, performability, operation readiness, design education, and so on. So if you see how they have given the holistic view of system effectiveness. So system effectiveness is defined as a problem. It is a probabilistic measure, which has its three components. They are also measured in probabilistic way. So a system can successfully meet an operational demand. On a general level, you can say this is the system effectiveness. And other part, if you see that this is system technical effectiveness, STE, or system operational effectiveness, another term. So as availability has been defined as a general term, and depending on the what are the downtime components you are incorporating, the availability definition changes like achieved availability or operational availability. Likewise, system effectiveness also can be defined depending on what you are taking into account. If you are taking the inherent capability, inherent properties of system like reliability, maintainability, and supportability, then that gives you the system technical effectiveness. But if you incorporate the utilization process of a system, which is driven by the operational scenario and the maintenance policy followed, then it gives you the system operational effectiveness. Now coming to this, the design adequacy. A system is designed to meet certain design objective. So probability of meeting those design in objectives is known as design adequacy. Recently, you have seen that the ISRO chief has claimed that 95% of the Chandrayaan-2 objectives have been fulfilled. So we can call that design adequacy. At the same time, mission reliability is given as once the system has started in certain mode, it will complete the mission in that mode. So this is again on a probabilistic basis. Third one is the operational readiness. Again, it is a probability that system will operate in the mode for which it was designed. Sorry. At any point of time, system can be made either found to be either in operable state or it can be put into the operation. So it can be in storage where it is presumed to be in operable state. The presumed word is has emphasis on, where on this the system is in the operational state but is not being used. It is in idle state or so. The third term, which is availability, which has already been defined by Dr. Rajesh, I'll just give you an idea that availability is a component depends on operating time, and operating time depend on the reliability, because once the system is operating, its completion of that mode depends on the reliability part that we call that it is related with the mission reliability. The other component of reliability is the downtime, which is a function of maintainability, how easily, how fast you can, the probability of restoring the system into functionable state. And this maintainability has several downtime associated with it. Active repair time, if you see the repairability and maintainability, they have similar definition, except that in repairability, we only consider the active repair time. And active repair time depends on the serviceability, where how fast, with what ease we can restore the system. The other downtime components are logistic time, where we try to see, we are waiting for certain special parts or certain queue members, so it becomes the logistic delay time. And administrative time basically related to the various decisions are to be taken, like which crew team is to be sent out, or other. So this is just I explained that the total time has operating time. This I have. So why reliability engineering? Practically all the contract documents nowadays, you will find they are having certain reliability and maintainability clauses in their specification. And this requires the understanding of those terms and terminology with respect to the reliability so that they can be interpreted correctly. Second is complexity of the product. You will observe that day by day, the complexity of the product is increasing and the customer demand is increasing to embed more functionality, sometimes driven by the requirement and sometimes driven by just for the sake of having those facilities. So for having a high complex system to be reliable, their components and their lower order should also be highly reliable. Another thing, many of the products you will find advertised by the reliability and maintainability characteristics, and that forces competitor to know their RAM characteristic. They should also find out how to generate such kind of data to quantify those RAM characteristics. Besides, learn how to quantify them and how to interpret such ratings to advertise correctly to have an edge on their competitors. Another thing you will find that concept of caveat emptor. Earlier, this caveat emptor concept is not valid nowadays. The meaning of this was initially it was the customer or the consumer's responsibility to assess the risk of using that system. So this is not valid nowadays. A company is liable for its product, legally responsible for its products. So anything is happening, company can be sued for such failures or consequences of failure of that project. Likewise, recent standards are moving towards absolute liability. Even a designer, a manufacturer, a store, a distributor can be sued for any failure that is highly risky or so. So it absolves the user. So in other words, even this person can be sued and has sued for causing any harm to a community or the system. You can recall the Bhopal tragedy and Nokia battery replacement case for the same. So in this context, how the reliability engineering is going to help you. So the reliability engineering that provides the theoretical and practical tools to quantify the capability. In fact, I used the term earlier, capability. Even initial reliability definition, if you go back, is the capability of the system to perform its intended function. Now the question becomes how this capability can be quantified. So the common language was found out is the probability, because every engineer can understand the probability of success of their own system, whether it is electrical engineer or civil engineer or so. So it can be quantified in terms of the probability of chance, and which can be specified, allocated, designed in. That can also be predicted before the product is coming into picture. It can be monitored, it can be tested, it can be estimated. And again, I am using the predicted term. Here, the predicted, when the system has not been in physical sense, but here it is estimated and predicted for the system which is already is existing. It can also be demonstrated to the customer that yes, the reliability, it has a particular reliability label with their maintainability, availability, safety, and quality label. Parallel to this, there is maintainability engineering. If I just change reliability here, REE, ME, maintainability engineering, and read it like this, so you will find that maintainability has a parallel space. Like maintainability can be specified, it can be allocated, it can be designed, and it can be predicted, and so on. So if I just to say that reliability engineering, and there is a parallel branch of maintainability engineering. So what the benefits of reliability engineering is going to give you? It is becoming a customer requirement, where customer definitely demands certain functionality, and that should be reliable. And if they are not working properly, the irritation is caused, annoyance will develop, and company reputation is going to be on a stake. A company reputation is depending on highly on reliable products. If the products are reliable, then definitely the customers are going to buy again and again the products floated by those companies. So the company will get the repeat business. Besides, they are going to have a competitive advantages on their competitors. You know that warranty cost is very much affected by the number of failures. If the failures are high, definitely the company has to keep some warranty reserve fund. It has to open some kind of repair center at the local level, at the next level, and that involves cost. So what if the failures are captured, definitely the warranty cost can also be curtailed down. Customer satisfaction is definitely, if customer is not satisfied, it is an old saying that one dissatisfied customer takes away another 10 customer. So customer satisfaction for a company is a very big issue. If the customer is satisfied, it is going to get repeat business and other advantages. So considering all these factors, the failure consequences and the benefits of reliability, then there exists how to establish, how to see that these reliability goals are to be specified. In other words, I am concentrating on only the first uh, letter of RAM, reliability. So this way I am switching over to my next part, reliability. In the system effectiveness, you have seen that the reliability is coming out, the maintainability is coming out, and availability is coming out. So I'm from India. So I'll say in the Ramayana, there is Ram and there is Sita. So RAM already coming in the system effectiveness module, but S is missing, means Sita is missing. So it does not mean that reliability and maintainability, in fact, implicitly addressing the safety issues as well. You remember that all the failures are related with the safety, and all the failures, you cannot say they are safety related, but many of the safety related issue can be resolved once one go for proper reliability and maintainability study of their system. So coming to the reliability, the next part of my lecture, the reliability specification. Reliability, first a brief look at reliability design. You find this kind of flow chart in various textbooks where the system reliability in design, or for any design process for that matter, is an iterative process where we specify the reliability goal in the reliability context, which are consistent with the performance and the cost criteria. And this should be related to the life cycle cost and what reliability is going to have an impact on system effectiveness. So once the reliability goals are specified, they are to be percolated to the other parts of the system. At the very preliminary stage, you will find that the system is becoming a series model in reliability. So those reliability allocation can be done. There are methods available, and as the design improves, or design will involve, one can go for the reliability block diagram analysis and the corresponding allocation. And once the allocation is done, the various reliability implement design methods are resorted to. And these methods can involve the proper selection of parts and material, identification of technologies, stress strength analysis, derating, use of redundancy. So these some of the design methods I have say indicated here. There could be many more reliability-based design methods. So once the design methods are implemented, design has been reaching up to a stage, one can go for in parallel failure analysis, where the FMEA, FMECA, reliability growth testing, if the prototyping stage has been reached, one can go for the reliability growth testing, or some of the time you are trying to find out what would be the possible failure mode in the application areas, and some of the time you are just finding from the drawing itself what will be the possibilities of failure of the system. So these kind of analysis are done, and based on the testing of actual system, then one can assess whether the reliability goals are achieved. If they are achieved, then one can go for the look for the validation and verification of the safety margins through the tools like FT or so. And once they are also met out, then one can ready for production. Otherwise, this goes on to improve the system and so on. So the reliability, Dr. Rajesh has given you one of the definition as the failure-free operation of the system, the simplest definition. However, if you see what are the components of reliability, it is a comprehensive definition. It is a conditional probability. This conditional word is missing in many of the definition. At a given confidence level, you will not find this word in normal definition, which you find in the textbook, that the equipment will perform its intended functions satisfactorily or without failure for a specified length of time when used in the manner and for the purpose intended. Again, this underlined word you will not get. That's why I'm saying that is a comprehensive definition. While operating under the specified application and operation environment with their associated stress level. So one is the simplest definition, another is the complex, comprehensive definition. In between this, it is the IEC, International Electrotechnical Commission, which has also floated several standard on reliability study or analysis. They have given a definition which already presented by Dr. Rajesh in his slides. And or otherwise you can find in several books. So how to develop good reliability specification? That is the question many of the time you will find once you do the reliability studies. Even the most vigorous reliability testing program will be of little use if the product being tested has a very poorly defined reliability requirement. Why it is happening? Sometimes you will find the reliability requirements will be developed by a group which are not at all conversant with the reliability concepts or reliability data analysis. And this results into a very vague and unrealistic requirements that do little to aid in the development of the product. Another is, while most organizations are concerned with the reliability of their products, many will not be able to develop a very good reliability specification, and that becomes a serious flaw that can result in unreliable products are reaching to the market. So many of the times, if you see what could be the possible reliability specification, generally you can get in the requirement document. A new product will have a reliability that is no worse than that of the previous model. This is one of the statements you can hear. Another statement could be the product will meet or exceed customer expectation. Now, if there is no quantitative information about the previous model, which is worse, which is good, how one can determine? And if it is to exceed customer expectation, then what is the measure of customer expectation? Another question one has to pray. But this may be useful as a general guidelines, but they become codified in the requirement documentation for the project as the reliability specification, which is slightly wrong concept. So essential elements of reliability requirement generally have 4 to 5 components. One is it should be measurable, which can be translated in terms of the probability statements, the probability of success or so, with a desired confidence level. At what confidence you will say that your product is so much reliable, how much reliance you are going to put into, with what confidence. And it also, confidence level also captures the variability in the data once you are estimating the reliability, and also it addresses the sample size issue. We will see later what is meant by. Another is duration or time, or we call that mission time or operational use, and so on. The fourth component you will find operating environment, and the fifth component you will say that customer usage profile. So operating environment can be put into either as a constant value or between the limits. Constant value means 25 degrees centigrade or so, using a limit plus minus 220 volts, something like that, or using time dependent user profile. These are the components. But at the basic level, at the essential level, there must be 3 components for specifying the reliability requirements. At a minimum, one should be the specified reliability, that is probability of success. Another is time over which it should be associated, and a desired confidence level. This definition has already given by, so many of the times when the system design is taking place, it must be adhered to what failure definitions you are following. Likewise, these definition are, you can always quote the standard, because many of the company wants that you follow some standards. So one can follow IEC standard or MIL standard. There is a requirement. So these failure definitions are related to the failure, and this is related to the process failure, equipment failure, unable to produce the confirmed product or so on. My idea of given this, once you are recording the data, there is a failure categorization. You must know that what is failure, what types of failure you're governing with, and they must be recorded in a proper manner. So failure criteria, intermittent failure, where when the condition exists, the system, such kind of failures are only occurring. The extended types of failure require some kind of corrective action. And this extended type of failures could be catastrophic, which are the component complete, that is complete stoppage of the activity of the system, and they're sudden, they're appearing without any warning. Rather, degradation is you will find a gradual pattern where you can get the warning signal and the partial loss of function of the system you will observe. So this is just like show you, while data recording, you must address this kind of failures. You must know that what kind of failures you are recording and what is a failure occurring in the system. Another is, again, this is a slide. This is again for the, once you make a template for data recording, these are the things must be kept in mind, that the failure causes are to also be properly recorded, whether they are related with the design, whether they are related with the manufacturing, or whether related with the use, the operational scenario. So these are going to be helpful to address the failure and the failure causes, and hence they improve the design. So these are the just explanation of this various types of failure. So another question which I try to say, if somebody wants to set the reliability goals for their system, there are possibly three methods. And one, you can formulate the problem as optimization problem, where you can calculate the reliability of several different configurations, or you can alternatively or combine with the same configuration with but different state of the art component. So use of different art of the component with the same configuration, or different configuration, you can create the reliability configuration, and the total cost you can compute based on the usage of. So this is nothing but the LCC cost estimation, and find and select the, in this manner, you can plot it reliability of different configuration. Configuration 1, what is the reliability and the corresponding cost. Configuration 2, what is the corresponding cost of this system. And you can have a plot kind of thing where you can select the minimum cost criteria, and you'll find that configuration 4 has the minimum cost, and the reliability is, you can set this reliability as your targeted reliability. Another method, which can be components failure rate, and using databases, like there are several databases are existing, or the guidelines are existing for predicting the failure rate of your system based on the component failure rate models like 217 plus FITES. You can have the database failure mode and failure mode distribution database. Right now it is 2016. You have the database like EPRD, NPRD, and this is another. This is Group of Industry Data Exchange Program. This is a consortium of different industry. We are sharing their information. You can find the details of this GIDP. One should be a member of this on their corresponding site. So one can predict using a multi-valued prediction. Many of the times you have the failure rate, the best failure rate, the lowest, high, most likely failure rate you can find in these databases. Based on this, you can evaluate what or predict the reliability of your system. So you are going to get three values. And if similarity based, if you're not finding the exact component in this or model in these databases or guidelines, you can subjectively modify such failure rate for the state-of-the-art components for which failure rates are not available, and then you can select the target reliability somewhere within the predicted range. So at a very exceptional case, you can select the upper limit of predicted reliability. So these are the two methods one can follow to target reliability. But if these two methods are not working at all, then you can go for the system reliability in excess of 85%, or preferably in the excess of 90%. So it becomes a apportionment type of method where you are setting a target reliability at the system level, then allocating the reliability on the subsystem or component levels. So once you develop this reliability, now we see the three components which I said, the essential component, how you are going to specify. The first, you will see that usually you will find that the life or the reliability metric is specified in terms of either the mean time to failure or mean time between failure. For instance, this is 10,000 miles. 10,000 miles. Yes, please. 10,000 miles, or in terms of the failure rate, it is 0.001 failure per mile. So what most of the time, how it is interpreted, and many of the engineers will find that they will say that possibly their interpretation will be that most of the system are surviving at 10,000 miles. Is it a life? And MTTF, if you are confusing with MTTF and MTBF, the MTTF is generally used for the non-repairable system, and MTBF is used for a repairable system. This is the general difference you will find, and in most often, if you go for the modeling side, then the MTTF, if the exponential distribution can be modeled the time to failure, then you can say that this mean time to failure, you can say, or okay. So most statement of the MTBF are in terms of hours or kilometer or cycle. Easy to confuse with MTF. So once people are giving in terms of the days or years, then this specification is usually confuses that it is going to be live, which is not the case. So what the requirement writer thinking that random failure or exponential distribution is the model through which one can model the time to failure or time between failure of the product. So difference between MTF live, you can very well guess from this curve. If you analyze the population where you collect the data, the failure data of that, and you plot this data, the cumulative number 4 versus time, you will find that this kind of curve you will obtain. That initial very early failure, then there is a stable period, and there is a rise of this number of failures. And if you model this in terms of failure rate, you will get a very common and very famous curve, which is known as Barton curve, which is the curve between failure rate versus time, which Dr. Rajesh has also shown you. So this curve shows a period of relatively very high failure, followed by a constant, and then there is a third period, what you call that, due to wear out, this failure rate starts again increasing. So useful life not begin until this. If you remove this part somehow through some testing, through some filtering process, then the useful life of the product begins like this, and this is followed by this. So MTBF, MTTF, what we talk about, it is the inverse of failure rate during this period. If you are removing this and that, while the product is following all the phases. So the MTBF will give you an indication. You will consider that this is becoming the life without considering this period and this period. So this is defined as the reciprocal of the failure rate during the flat portion of the failure rate curve. So MTBF or MTTF are defined in terms of this portion of the curve where the useful life, we consider only the useful life. The unit of failure rate is failure per hour. the unit of MTBF, then it becomes hours per failure. Now note that it says nothing about how, up to what point the first phase will last. How high the failure rate during this period, when this failure rate or the wear out zone will begin. So MTBF has no correlation with the onset of the variable. So it is not at all related with any of the first portion and the third portion, but only you can relate it with the middle portion. So, and if you compute the reliability at the MTBF, it turns out to be 36.7% only, or 36.8% only. So once you are specifying this requirement, are you thinking in this? Possibly not. Nobody wants that reliability after 10,000 is going to be 37% or so. It must be very high. So let us take another example, that how MTBF will mislead you. So suppose there are 8 units are to be tested, and the supplier has given the following data. If you compute the MTTF of that using Weibull analysis, so you will find both the supplier's product are providing you 10,000 miles MTTF. So which one you are to select? Are you going to select anyone? So based on this reliability time matrix, the two suppliers' reliability can be considered to be equal. Now let us see that how the reliability varies with respect to time. So in the first case, say, so at 10,000 miles, you will see the reliability is vastly varies from supplier 1 to 2. Supplier 1 reliability is coming out to be 36.79, where the supplier 2's reliability is coming out to be 59.2. So this is the supplier 2, which has better reliability than supplier 1. So if you say that 50% chance of success, of 50% with 50% confidence, what is the reliability? Here you can see the life of the product is. So you will find the supplier 1's life with 50% confidence is 6930, and supplier 2's life is 10,066 miles. So in other words, supplier 2 is closely matching the requirement, not the first one. So simply taking the MTTF as a reliability matrix will give you a wrong notion. So the use of MTF can easily mislead a design team or contractor into the producing low reliability designs, as you've seen in the earlier slide. Likewise, possibly you can save some money on your test to prove that yes, MTF goals are released, are proven. So in short, attempting to use a single number to describe an entire lifetime distribution can be misleading and may lead to poor business decisions. Let us take another example extending the previous example, the beaten life, where beaten life could be either the design life, warranty period, or whatever operation uses life is equal to 10,000 miles or 90%. In other words, we expect a 10% failure over 10,000 miles. So it is a better matrix, as it does not make the exponentiality assumption and it states clearly the percentile of failures by a certain time value. But certainly it lacks one component of reliability specification, that is a statistical confidence attached to. If you are estimating the reliability of that particular product, then how confident you are that the reliability is matching with this. So we can change to attaching a confidence, 90% reliability at 10,000 miles with 50% confidence. So if you're plotting this, if you're saying that 50% confidence, then it is as good as not to quote it, because whatever analysis is done and reliability data analysis, they are done at the 50% confidence level. So just one example, see this. So design A, the failure times are, there are 20 units which are tested and all have failed at different times. Likewise, the design B gives 4 units tested to failure. Now, if you see the plots, the reliability plots, unreliability versus time plots. So if you see that the probability of failure here 5%, right? It is well below. So 90% reliability, we'll find that both meet the reliability requirement at 10,000 miles, because this is 90% reliability, the probability for failure should be 10%. So well below this, both are meeting the reliability, and design B has around 0.96 and design A has 0.95 at 50% confidence level. So both are meeting the design, reliability. So anyone can be selected. Now, if you look at 90% reliability, we see that, as I said, the 50% confidence level, as good as not to specify that. But if we specify the reliability requirement as 90% reliability for 10,000 miles with 90% confidence, it means we want a minimum reliability as 0.9 with 90% confidence. Now, the statement, same as previous example, you see that, except that more confidence is put into. Let us see the previous example, where we have the 20 units to test and design B has 4 units to test. Both are giving the same, almost close to same reliability. But given this requirement, you see what will happen. Now, the lower confidence interval has been drawn. Red line and this line on the previous graph. If you see that, at 10,000 miles, the 90% lower bound of reliability for design B is 79. This is the confidence bound, because it is just as 4 unit, so uncertainty is very high, and hence they have the confidence bound wider from the main. And the design A has 90.41% reliability at the lowest level with 90% confident. So design A meets the requirement, which is much better than the design A. So up to previous example, we can go up to that. That will suffice the requirement. However, if you want to extend it, then one can specify 90% reliability for 10,000 miles with 90% confidence for 98th percentile of customer. Now, if your product, if you see that your product is going to be used in a variety of stress environment, say for India, the environment changes from cold to very hot. If you want the same product to be used, then that has to be tested at various stress level to satisfy the customer base which are residing at these varied environment. So then you will have to test your product. The testing cost is going to be very high, because you are going to test your product at a variety of environment and stresses. Then only you can say that. So this is just explanation to that what is the meaning of 98th percentile customer. It means variety of stress level you have to test it, because you have to satisfy the customers living at various geographical region, or you can say varied environment, and your product has to be used by those customers. So with this, so there are another area, the accelerated live testing, halt test, through which you can simulate these stresses and find out the failure modes or to quantify the reliability of your product. So coming to, possibly I am just in time, possibly, but overshooted another 5 minutes or so. So in conclusion, I just wanted to say that I wanted to convey this. The one question is the system effective. The earliest definition of system effectiveness contains the RAMS, what we are talking out, and there are certain questions like how to specify the reliability for your product. This question, how you can address, what should be the proper metric, not this MTBF, MTTF is not the correct metric for specified reliability. Or if you want to set out some target reliability for your system, you can go for 3 methods which has been discussed or briefly discussed in this webinar. With this, I conclude my lecture. Thank you very much for listening me. I had to, because of the time constraint, I had to skip many more things. Thank you very much.
Thank you very much, sir. It is always a pleasure to listen to you, and today you have actually told us about in depth about how to find out the reliability and all. So this is very informative. In fact, we have received comments from a lot of participants regarding it, and in future also these participants can always contact you. Thank you, sir.
Thank you for the nice words. Otherwise, I know that I missed many things. I had to escape
I
my
know because
words.
I
I
have
had
seen
to
your
put.
slides on earlier presentation. So I assure that the participants all can always get back to sir for more
Thank you.
insight into his presentation. Thank you, sir.
Thank you very much. Thank you. Thanks a lot.
Now I invite Dr. Perry Dursin sir to share his presentation. Let me give a brief introduction of Perry Dursin sir. Professor Perry Dursin was born in Belgium and graduated from Massachusetts Institute of Technology with a PhD in electrical engineering. After receiving a master's degree in operation research also from MIT, he worked on reliability of large electric power networks as part of large-scale system effectiveness analysis program sponsored by the US Department of Energy from MIT Control Incorporation. After some time with Fabricom involved with fault diagnostic systems for factory automation, he joined Elstrom Transport in 1990. With Elstrom Transport, he has occupied several positions, mainly involved with RAMS and maintenance, and he founded the RAMS Center of Excellence. He is now RAM, Reliability, Availability, Maintainability Director, and PHM Director, Prognostic Health Management of Mobility. In April 2019, he was appointed adjunct professor for Louisville Technical University, Operations and Maintenance Department. He has contributed a number of communications and publications in scientific conferences and journals in the fields of RAM and PHM, automatic control, electrical power systems, including IEEE transactions on automatic control, IEEE transaction of power, apparatus systems, ESREL, almost on every RAM symposium since 2009. Several of Lambda Mu Symposia 2012, IEEE PHM Conference, and WSC 2013. He served on IEEE Reliability Society ADCOM and chairs the IEEE Reliability Society Technical Committee on System of Systems. He is a contributor to 4 chapters in the Handbook of RAMS and Railway Korean practices, which we might have all gone across, those who are from the railway. In January 2020, he was awarded prestigious State Award by the IEEE for his tutorial designing for the availability of system and systems of systems. We are very fortunate to have you over here, sir. Welcome, sir, and we are eager to listen to your presentations.
Thank you very much, Dr. Vidushi, and good afternoon to everyone. Good morning for some. Now, first thing, can you see my screen, please?
We all can see your screen, sir, very well.
Yes, full screen? Okay, good, excellent. So, again, thank you for inviting me today. I'm very glad to be with you. So I will speak about prognostics and health management for railways, experience, opportunities, and challenges. Just a few words about Alstom. Alstom is a large OEM in the railway industry, present in more than 50 countries worldwide, including a very strong presence in India. We are active in rolling stock signaling systems, but also services. And of course, this is the reason for our interest in the maintenance topic. So I'm as Dr. Vidushi said, I'm the PHM RAM Director for Alstom Digital Mobility. So the name indicates you already have an idea of our scope, but it's mainly signaling and accelerating the digital revolution, let's say. So we'll be discussing the benefits of predictive maintenance, PHM methodology, its enablers, some words about the links between PHM and RAMS, and we'll illustrate with some railway case studies. So this is the outline of my talk. And first of all, as we all know, RAM is one of the most eco-friendly transportation means, and in today's world, it's very important. But we are confronted with big challenges, controlling operations and maintenance costs, and also ensuring performance. That means punctuality and availability. And it's a real challenge to meet those goals. which are sometimes conflicting. Some railway companies say that in order to survive, they have to cut maintenance costs in half. Maybe it's an exaggeration, but there is a real challenge. So this is true in a large number of complex systems, not only in rail, because these systems are confronted with increasingly demanded RAMS targets and at the same time in a very competitive environment. So life cycle cost is a key competitiveness factor. So the question we are going to address is how to make maintenance smarter to combine quality and competitiveness. And in that context, what can be the role of the digital transformation that we are all living through? How can we leverage it? Just a reminder of, the standard from IEC about maintenance. Basically, there are two kinds of maintenance practices. Corrective maintenance, which is after the failure, and preventive maintenance, which is before. But preventive maintenance most of the time consists of predetermined maintenance operations, determined or scheduled based on mileage or time. And instead of that, you can do condition-based maintenance where the decision to maintain is based on the condition or state of the asset. And within that category, there is a special case of predictive maintenance, where not only are we interested in the current state or condition of the asset, but on predicting how this condition will evolve with time and adjusting the maintenance operations accordingly. So why should we do predictive maintenance? Because we want to reduce the number of service-affecting failures and thereby increase regularity, punctuality, and availability by reducing the downtime induced by maintenance. But we also want to cut unnecessary systematic maintenance and thereby reduce maintenance costs. In the end, we'll have a higher asset utilization rate, and last but not least, we'll reduce personnel exposure to hazards, because if they do less maintenance, they are less, of course, exposed. Prognostics in health management is a term that was coined in the early 2000s, around 2000, 2001, especially in the aerospace industry. And it's the set of techniques and tools that enable predictive maintenance and that support corresponding decisions, what some people sometimes call prescriptive maintenance. There are three steps which are actually progressive difficulty, shall I say. First of all, detecting that there's an abnormal behavior of the asset, or detecting that there's an incipient abnormal behavior, that is, there's a degradation phenomena underway. Then diagnosis, determining what type of degradation, its localization, where it is, and how severe. And finally, prognosis, estimating the remaining useful life of the monitored asset. Is how much time do we still have to the real failure if nothing is done? We can also look at that as a conditional probability of failure, but over a certain time horizon. So within Alstom, we have developed a system. So now I'm going to speak about developing a PHM system, and in a second phase about operating a PHM system. In Alstom, we have we have put together this methodology in 5 steps to develop a PHM system. We start with the user requirements and then go through technical design, prototyping, which can be bench-based or virtual, then demonstration and field demonstration. PHM user requirements, we ask questions such as, of course, we start with the expert knowledge, as Professor Kumar said in the beginning. Of course, we really have to capitalize on expert knowledge, and then comes the data. We look at the life cycle cost analysis and the FMEA, which is failure mode and mechanism effect analysis. Not only in which way the system can fail, but what are the mechanisms that cause degradations and later failures. Then we identify the key physical parameters that we want to monitor and that are going to tell us about the unfolding failure mechanisms. And this determines the hardware and software architecture. Hardware architecture such as where we need sensors perhaps, software architecture, how we communicate the data and so on. The core of the methodology is this part, where we have either a test bench where we actually trigger degradations based on the early analysis. And it can be also a virtual prototype where the degradations are actually simulated in a software model. So that's really a digital twin. And we generate health indicators that actually are a measure of how healthy or unhealthy the asset is. And in these experiments, we are validating the health indicators in normal and also in degraded conditions. So we make sure these health indicators are a good metric for detecting and diagnosing the failures. And then once we have done this in the lab, we still have to demonstrate it in the field. So once we have developed a PHM system, we can operate it. And there are several stages, of course, in operations. First of all, acquiring data acquisition. We have to be sure that we know the context, as was emphasized by the previous speakers. Context is extremely important for reliability. And then we pre-process the data. Sometimes the data is not clean, we have to clean it. Then we usually do some signal segmentation, feature extraction, which means a sort of summary of the signal. We feed in the expert's knowledge. And then state detection consists of deciding whether currently the state is healthy or degraded, whether the degradation is ongoing. In that case, we have to diagnose the degradation, isolate, and assess the severity. And then if we can, we do prognostics. Sorry, too fast. We do prognostics, and we advise the human operator, the maintainer, on the best decision that he or she should take in view of all the knowledge that we have acquired. In other words, we tell him what he should maintain and when. And so this sequence of steps is actually standardized in ISO 13374, which is a standard for asset monitoring diagnostics. So you recognize the various steps: data acquisition, processing, state detection, diagnosis, assessing degradation level and its severity, identifying the mechanisms, prognosis, estimating the remaining useful life, and advisory generation, generating recommendations for operations and maintenance. Now, there are, fortunately, some technologies which are actually enablers to this predictive maintenance. And these are, first of all, the ability to capture data in the challenging environments that we know in the railways. Then we have now a huge variety of cost-effective sensors, wireless sensors, the Internet of Things, that can communicate in almost real time all sorts of physical variables that we are interested in. And the connected trains, these variables can be sent from train to ground or in almost real time as well with our communication networks. Then we can store and manage those data and make use of the huge advances in machine learning and more generally artificial intelligence. I will not dwell too much on this, but just to say that AI is something that's been going on since the 1940s. The idea is to attempt to understand and replicate human cognitive functions. It's a very, very wide topic. But the subset we are mainly using is machine learning, the ability for a computer program to perform tasks for which it has not been explicitly programmed. And a subset of that is deep learning, which you may have heard a lot mentioned in the media, but it's something it has a very technical definition. It's based on multi-layered neural network, and you can learn feature levels of increasing abstraction without human intervention. Next to that, we have a symbolic AI, which was an avenue that was pursued a lot before and still pursued. But so therefore, if you look at the entire scope of AI, it contains all of this, of which machine learning is a subset, and inside you have deep learning. So we use mainly this. But so just to illustrate, machine learning is the ability for a computer program to perform tasks for which it has not been explicitly programmed. In the traditional approach, you have inputs, you know the models, and the computer generates the outputs. In the machine learning, you have inputs and outputs, and the computer learns the model. So this is something very difficult, but for which algorithms have been in existence for several decades, only they have only been made practical recently through the incredible advances in computer and communications that we have known, in particular in the last 2 decades. So machine learning is good, but you also need expertise, and we combine both. In the 5 stages that I've outlined, we do use machine learning to extract information from data and combine them with expert knowledge to perform detection and diagnostics and prognostics. The virtual prototyping approach is very good because it is software-based, so it is much more flexible than hardware, and it reduces the cost of experiment. Then one thing that we must emphasize, it was emphasized also in reliability, we have to deal with uncertainty. There is uncertainty in the model, there is uncertainty in the measurements, and there is uncertainty in the future load to which the assets are subjected. So we do have to use Monte Carlo simulations and the like. Never give just one word, one figure for instance, remaining useful life, but always a confidence interval. So we start with raw signals. Now the naive approach would be to look at a curve which corresponds to normal operation. Let's say this is a current versus time, for instance, and to ask the expert to define rectangles or gauges around the curve, and if the curve exits those gauges, then an alarm is triggered. But this is naive because you can usually have too many false alarms or too many missed detections. So we replace this naive approach by one where machine learning models generate what we call health indicators, and we can quantify the probability distribution of those health indicators. And then we will have a threshold, but on the health indicators, not on the physical curve. And then we can control more the risk of error. So the health indicator, if you look at features, let's say the signals that we are monitoring are summarized by a number of features, and you look at the multi-dimensional space of features, then every condition is like a point in that space. And if the yellow cluster, the green cluster here shows the normal operation of the assets, and an observation is materialized by a blue or red point, then the distance between these observations and the cluster gives you the health indicator, which is basically a distance to health. So the higher the health indicator in our system, the less healthy the asset. So this is a visual way to show the health indicator. So it will be used mainly for detection and diagnostics, but then also for prognostics. And as we showed earlier, the prognostics, what is the prognostics? It's predicting the remaining useful life, in the sense that given a past evolution of the asset condition, materialized here by a health indicator, we are here. And we want to know how much time we still have before a full-fledged failure takes place. So this is the time the maintainer has in order to intervene, in order to avoid the failure. And so there's uncertainty on that time, and his challenge is to intervene not too early because it would increase maintenance cost, but not too late because then he would not be able to prevent the failure. So just a few words. There have been some very interesting talks on RAM. So just a few words, and this is consistent with what Professor Kumar said before, synergy between PHM and RAM. First of all, the first step in the PHM development is the FMMEA, failure, mode, and mechanism and effect analysis. And this is typically a RAM exercise, which is going to be the first step for the PHM. Then, once you develop a PHM system, the main benefit is to increase reliability and availability, and of course, that's RAM. So it's obvious that the two are related, but they are different. RAM focuses on populations and PHM focuses on individuals. For instance, in RAM, you estimate the lifetime as a distribution law for a population with an average mission profile and in context. For PHM, you forecast the date of function loss for one individual asset, the customized mission profile. In RAM, you deal with failure data, which is the dates of those data, discrete data. In PHM, you look at degradation data, so that's continuous parameters. In RAM, you make maintenance decision for a population. For instance, you would estimate the necessary amount of spare parts and the frequency of maintenance intervals. In PHM, you make the decision support, you make the maintenance decision for one asset. When do I maintain this asset? In RAM, you deal with global indicators like the MTTF, which has its weaknesses, as reminded by a previous author. Also MRL and mean remaining residual life, the failure rate. And in PHM, you have the remaining useful life and the health indicator. The expectation of the remaining useful life is the mean residual life. And so I think that many of the works that have been going on, let's say a lot of the precious heritage of RAM engineering is useful potentially for PHM. But the two communities are usually separated, and I think there is room for a lot more synergies. And by the way, I'm glad to see that in Gautam Buddha University in Noida, it seems that this synergy exists, as it also exists in Luleå Technology University, for instance. So now we are going to look at case studies, of course, railway case studies that I've been involved with. Alstom has been involved with all those systems, but we don't have too much time, so I've made a selection of 3 subsystems, the point machines on the signaling side, the HVAC and the doors on the train-borne side. So first of all, turnouts and point machines. Of course, you all know what a turnout is. It's a mechanism that allows the train to change direction, and it's controlled by so-called point machines or switch machines. It's important because it has a big impact on network reliability and availability. We know that a turnout failure can make an entire line unavailable, so it can have tremendous consequences in terms of punctuality and availability. And usually it leads to penalties and, of course, negative image. Also, they are an important cost item in terms of maintenance. The maintenance is usually performed manually quite frequently. So, by the way, it also takes place at night, and so it's not the best conditions for the maintenance agents. 2 reasons to investigate predictive maintenance. So how to do it? So what we have done is we monitor typically the current as a function of time during an operation, that means a maneuver, a swing from one position to another of the turnout. And this is a normal shape of that curve, and we segment it. And for each segment, we calculate what we call a feature that is basically a summary of the signal on that segment. So the summary can be different depending on the segment. For instance, in here, you can see that the slope is probably relevant. In here, maybe it's the average and standard deviation, and so on. So then with all those features, we create, as a mathematical operation, a scalar function of all those features, which is a health indicator. And in this example, we see that the health indicator evolves in time, which means that the condition of the turnout deteriorates. And by the way, after there is a maintenance intervention, the health is restored, which is good, which is a goal of maintenance, and therefore the health indicator comes back down to a normal value. So the benefits are those I mentioned. By the way, in one example we dealt with, they increased the maintenance frequency from 1 month to 3 months, but the real goal is to do away with systematic maintenance. And for diagnostics, we look at what we call signatures. And a signature is a set of values, basically is a whole vector of features. So you see that different signatures correspond to different failure modes. Failure because of lack of lubrication, like loss of tolerance, that is the adjustments, rail deformation, power supply problems. So by looking at the current signature, we can compare it with the various signatures we have in our library, and therefore deduce what the main or the most likely type of degradation is. So that is basically diagnostics. And this is a real example. We start by a training period, which can be of variable length, but long enough to teach the algorithm, to teach the machine learning algorithm, the normal operation. So it has acquired a number of values of the health indicator that corresponds to the normal operation. So we have to be sure it is the normal operation. Then these are the observed values of the health indicator in the subsequent period. Every point here in this space corresponds to a curve on the right. So a physical curve acquired during one maneuver, current versus time. So you see here, this point corresponds to normal operation. This one's already slightly degraded. This one totally failed because we lost control of the turnout. So of course the goal is to intervene here before you get to this point. In that case, the maintenance told us that the cause was an inadequate adjustment. So this was for turnout, where we had, I didn't say, but we had a physical test bench. And now just a few words about another application, which is heat ventilation and air conditioning, HVAC, for which we decided to use a virtual prototype, because a test bench would have been very expensive. And also we had all the thermodynamic models that allowed us to model the operation very precisely. So then here I'm going to focus on the filter, which is one part of the HVAC, but one very important part. The failure mechanism is that as time goes by, the filter clogs. It's clogged with dust, and you see the difference between a clean filter and a clogged filter. And what happens then, of course, is you need to, in much more important throughput, airflow, to achieve the same cooling capacity. So the so-called coefficient of performance, which is the ratio of the cooling that you get over the energy that you inject, goes down. And so on that basis, we can build a health indicator which basically measures the percentage of loss of the cooling capacity. And therefore, on that basis, you can forecast when the function will be completely lost. The reason why HVAC is important for preventive maintenance is that it contributes to energy consumption. It is a high maintenance cost item, especially because you have to work on the roof. And the impact of a fault is important. You reduce fleet availability, and in hot countries, it reduces passenger comfort. In some countries, like in Dubai, when you lose HVAC, you have to remove the trains. So this is the evolution of the health indicator, built, as I explained before, with time. And if this is the present time, we are able to construct a confidence interval for the future values of the health indicator, and therefore a confidence interval for the remaining useful life, which is between this present time and when the health indicator crosses the threshold, which is dictated by physics. In this particular example, which was, we had a demonstration on the RAMS tramway in France, the filter life was extended by almost 100%. According to the supplier, the replacement of the filter should have taken place at this stage, and instead we comfortably continued until this date. So we also generated this is the remaining useful life, the prediction with a confidence interval with upper bound and lower bound. As time goes by, of course, the interval shrinks the closer we are to the end, the less uncertainty about the remaining useful life, of course. And this is the actual one. So we see the prediction was very good. This was the installation of the data logger and so on the tramway. And these are the results. This would have been the replacement according to traditional scheduled preventive maintenance. And these were the actual, in green, the actual replacements. So we cut in half the number of maintenance operations and the tramway immobile downtime. So that was quite good. The return on investment is undisputable. And now we have generalized this to a number of vehicles and fleets. Last examples for today, passenger doors. Why are passenger doors a subject for preventive maintenance? Because in terms of maintenance, they represent between 10 and 15% of the total life cycle cost, at least on tramways and metros. Because obviously, as you can imagine, the loss of the door function has a big impact on train operation, and not to mention the way passengers perceive the network and the way, therefore, the operator perceives the supplier. And so what we did in this case was to go through the physical test bench route. So on this test bench that you see here, we simulated, we triggered a number of malfunctions. And in doing so, we took the context into account. It's very important. The types of malfunctions we simulated are maladjustments, changes in lubrication, and anything that can affect the kinematic chain. It is the order of the motor is not transmitted to the leaf. The context is important because, for instance, if there is cant, that is, there is an angle, the train is not completely horizontal, obviously it's easier to open the door, and conversely, in the other direction, it's easier to close it. So if you make the conclusion that there is a problem with opening the door, actually it was because of the cant, it's a wrong conclusion. So the context must be taken into account. Like in the previous examples, the context was temperature, for instance. So, okay, this is the benefits is that we can anticipate the mechanical issues, adjustments, for instance, needed adjustments for the door, malfunctions on the kinematic chain. And we followed the methodology that I've outlined before. First of all, analyze the failure mechanisms, and this gave us an idea of which parameters we wanted to monitor. In this case, position of the door, time to open and close, and energy expended. That was obtained through the current. So we had to have some sensors to monitor the current because it was not immediately accessible from the motor. Then we simulated the door degradations, as I said before, while taking carefully into account the context. And then we acquired the signals here. You see the red signal is the position. As the door opens and closes. And in blue, you have the current. So we have a test signal database. We extract the features. We build the health indicator. And from that, we obtain the diagnostics and prognostics. And then, of course, we had a demonstrator, which is a tramway in Barcelona in Spain. And this demonstrator has shown that, first of all, the test bench has shown that we can have a very high performance in terms of detection diagnostics. So we have a high detection rate, which means that most of the time when there is a problem, we detect it, and a low false alarm rate, we don't raise alarms when there is no problem, most of the time. So the types of degradations which have been identified represent more than 60% of the typical service-affecting failures encountered on a typical project. That means this shows that the system is quite effective in terms of the performance of the PHM system itself. Now, to end with a few words on challenges and opportunities as we see them. And of course, it's not exhaustive. Challenges. It's not enough to build an algorithm. You have to make sure that the performance of this algorithm is sufficiently good. What do I mean? In terms of detection, for instance, if you look at this so-called confusion matrix, you have the condition which is predicted, degraded or healthy, and the real condition, degraded or healthy. So one has to minimize the false negatives and the false positives. False negatives, that is saying that the asset is healthy when it's degraded, so you don't detect the problem. False positive is to say that it is degraded when it's healthy. You raise a false alarm, so those two are no good. Diagnostics, we have to watch for a correct diagnosis rate, and prognostics, the accuracy of the RUL estimation. Another challenge is cybersecurity, because we rely heavily on wireless sensors and communications. All of this can be pirated, and now it's a real danger at Alstom, like in many other companies. We have a cybersecurity department, and we must prove that when we install all those sensors and communication networks, it does not, it keeps the risk of cyber threat sufficiently low. Another challenge is that the machine learning algorithms are sometimes quite complex. And because they are complex, some of them are really black box. You don't know what's going on inside. Sometimes it's difficult to persuade the experts that the decision is a correct one. And there is a trade-off between interpretability and performance. And unfortunately, the easiest to interpret, like linear regressions, are the lowest performance algorithms. At the one extreme, you have the linear regression. The other extreme, high performance but difficult to interpret, you have the neural network. So you have everything in between. So an important area of research is to make artificial intelligence easy to interpret, so interpretability. So I will end with the perspectives. When we started this in 2006, we had a thing called the train tracer, which we still have, which is basically a network with intelligent data loggers, event recorders to monitor the conditions of the train and send alarms, but nothing more. And as we have progressed, Alstom has what we call the Health Hub, which is a platform with all the PHM algorithms. And we are heading towards prescriptive maintenance and advanced asset management. So the vision is adaptive PHM algorithm that would adapt to the changing environment, to the context, to machine and to the mission profile, so relying even more heavily on machine learning. Dynamic maintenance, that is once we have all the health indicators and prognostics and so on, making the decisions in more or less real time, but by taking into account the needs of operations, because maintenance is one thing, operations is another. So that relies on machine learning, but also on optimization. Risk-based asset management over the whole life of an asset or a fleet, one is always confronted between the cost of maintenance and the cost of renewals and the risks of service affecting failures if you don't maintain or don't renew. So what is the optimum? Here comes issues of utility decision, decision theory, and always cost-benefit analysis. So this is this area. And the vision of the future, the fully resilient system that self-heal when it detects degradations. And so then human intervention is almost no longer necessary. So you have to rely on the full-fledged artificial intelligence, but also control theory, etc., and reliability engineering. So this would be my vision, our vision. And I have added some references. There is a chapter on the handbooks of RAMS in railways, prognostics and management in railways. Example of the doors, example of the HVAC, and examples of the point machines. So thank you very much for your attention. I hope I didn't spend too much time, and thank you again.
It was a pleasure listening to you. Without talking much about the other things, move on to the next presentation because we are also running from the time limits. Dr. Dhananjay Kumar, I'll just speak about him also because he's a great person in this particular field. He is a great experience in this area. Dr. Dhananjay Kumar, he graduated from mechanical engineering in India and he earned a doctorate in reliability from Luleå University of Technology, Sweden. He worked as a senior reliability manager at Nokia, Sky Broadcasting and Sanofi. Currently, he is working as a reliability consultant for UK defense industry. He has a wealth of experience in improving availability, reliability of products processes throughout their life cycle. Concept, design, development, testing, manufacturing, launch, returns, and repairs. So he covers all the facets of RAMS, and we are very keen to hear from you, sir. Thank you for
Thank you. Thank you. I hope you all can hear me clearly.
Sure, sir, and we can see your presentation as well.
Yep. So this reliability assurance roadmap is based on my 25 years of experience in applying reliability theory in the product development, product maintenance, and declaring end of life or deciding the replacement of the system or product or a process. So I will cover in this topic, what do we do? How do we apply this whole reliability RAM or PHM from the starting phase, and how it follows through the whole life cycle of the product or system or a process. So, and I have not listed all the minute details in this roadmap. Only I'm trying to highlight the main events or main activities that should happen whenever you are thinking about a system, a product, or a process, whether it is a RAM or whether it is a PHM also. So in general, I will say that 6 main strategy wise, you should be looking at from the activity, 6 main activities strategy wise. And the starting when you have the initial phase of a concept, then what do you look at, like reliability requirements, reliability predictions. And then when you are moving into the development phase, you look at the how do you implement this design for reliability? How do you make this system reliable enough? And then what do you do to bring a confidence that my system is reliable before you start the operation or you launch the product or put the system in operation? And once you have done this operational phase or launch phase of the product, so you go through the reliability performance, reliability investigations, change. But the most critical one is this lessons learned during that journey. And then you bring back to any new product or even the existing product if you are still trying to create more systems. And then I will go briefly about what are the main challenges that we see in these activities and some examples from the telecom, from the defense industry, from the consumer electronics industry where I have been working. So the initial stage is this reliability requirements. And in defense industry, you have a very clear target defined, like in the fighter planes or even the emergency services, air services or road services or whatever it is. So they define it very clearly that what availability they need for the mission critical purpose, what should be the reliability, what should be the lifetime of the equipment, how quickly it should be repaired if something goes wrong. And sometimes they give you environmental conditions, but what they don't give you is the profile. Like if the fighter plane is going on just for 2 minutes above 100 degrees Celsius temperature, or it will be 2 hours above 100 degrees Celsius when it is completing its mission. So those are the lot of challenges that we get. And then coming back to the challenges side, the biggest challenge becomes like, how is it optimal cost to produce just 2 units or 10 units? How, to what extent we can define these reliability aspects of this product? So different methods that we use depending on if it is a larger population or a smaller population. Plus, sometimes you don't have a requirement well defined from the customer side, or you are creating your own product. So what I call it like internal requirements. And then as a reliability person, it's a responsibility to define those requirements. And I think the previous speakers have dealt very well. How do you define those requirements? But overall, it becomes like, do you see this reliability target, reliability requirements as an opportunity or as a risk? And that mindset brings us how much you can invest in making that product more reliable. Are you looking at the shorter gain or for the long-term gain? So this culture-wise in the business side, if it is a risk or it is opportunity, it makes a big difference. And that difference makes a here that what is the strength of the system you're defining and what is the expected stress or load on those products. And the distance between these two depends on perception, that is it a big opportunity for me to commercialize or monetize this opportunity, this product, this system, or is it just I have to meet the requirements? And some challenges becomes like just in a small example, like they ask 99% availability per month. So if I am producing 10 units, so I get around 72 hours MTTR, mean time to repair for that product. But if the customer is buying just 5 units, it means no failure should be allowed, because downtime is 36 hours only in a month. That makes very difficult analysis and focus on the design for reliability, depending on what quantity of the use of the system or product that we are developing. And this factor sometimes we do neglect, because some people say, you have already 99% availability of this system, and I just want one, I want 99%. So becomes a lot of conflict. So it's a lot of challenges that you try to sort it out or negotiate. So initial phase, we are still in initial phase. Some industry that don't define very clearly industrial initial phase or development phase, it can overlap between initial phase or development phase, depending on the company culture or the product development or system development process. But in general, this reliability prediction and reliability demonstration, this is the widely misunderstood area in the industry. Due to various reasons, there has been some team calling it there should not be any reliability prediction, because it's like a crystal ball where you are just giving a number without a proof, or we are not able to verify that. So normally for parts count method and parts stress methods for the hardware, one can use. There are various standards for that, how to do it. It's a very useful if you are just doing evolutionary technology to develop a new product. And then other area that is growing very fast is the software component reliability, because in the software there you have embedded software, and then you have a system software, and then other analysis software. So there are so many components come into picture that will ultimately reflect on your reliability of the system or product. And then other way we do is we look into this simulation side, you can do Monte Carlo simulations depending on this predicted reliability. And then you can look at the long term, whether it is if the target is within a month, I should have 99% availability. You should be able to simulate and tell to the designer, to the business that which area or which component is weak. And then you do the changes. Sometimes in the base stations, I had to do a lot of simulations there. We could improve the reliability of the base stations quite a lot by just improving a few components and putting some components in a standby and some K out of N situations, or in a series system or parallel system. Then comes this, once you have done the prediction, then challenges starts with this testing. How do you do the test? What confidence you can have? There are a lot of theory around it, but in reality, when you start to test, the product will be not ready completely. There'll be shortcomings. There'll be a lot of noise when you are starting to do this reliability test or demonstration to the customer. We had to do many demonstrations to our customer in Vodafone, T-Mobile, or even the defense industry in NATO, that the product that I have developed is reliable enough, or it will give me only one failure in 1 year of time. So in challenges becomes to agree on this, which method to use as per the which standards you have to use. In the test side, you have to look at the challenges becomes like, currently the products that our system that we design are very highly reliable, or the design in reliability is very high. So you don't get any failure during the testing. So you use the accelerated live test, highly accelerated live test. So there are various methods you use, but you need a lot of theoretical background to apply to come closer to the predicted reliability. So yeah, some of the customers still think it is a crystal ball unless until you have shown them through the test that this is the reliability we have achieved. And then comes from the initial phase, or when you are coming into the development phase, there are many tools people use for designing reliability. But what I found was that this failure mode and effect analysis, or failure mode effects and criticality analysis, both these methods give a quite good enough understanding of the product, that what are the failure modes that are likely to happen. Can we remove those failure modes using the design itself? Or if the design limitations doesn't allow me to eliminate those failure modes, can we do testability analysis, where can we do the monitoring or built-in test for those failure modes? And defense industry has been very, very good. So that has been quite good, well-established practice. But in the commercial industry, when I was doing one of the satellite receiver, you get so much data you can pull from the system, but the expense, the cost to analyze those data is huge. I mean, it's sometimes you can't believe even that how expensive it becomes to analyze those data, or to collect even those data. Those data are available, but the third party who support you to collect globally will become beyond your business benefit. So we need to optimize at that level. Challenges that happens, like from the design side, you cannot detect all the faults that the system can generate, or you have identified through this failure mode analysis. And since the availability requirements in the defense industry or other commercial industry is very high, so what do you want? You want to know exactly which system which part of the product to be repaired, which part of the system to be repaired. So that's where you use the concept of isolation. So normally fault detection, you look for the 95% of the different faults that can happen in this product. We should be able to detect. And then isolation side, you look at the at least 100% is the target. People say that I'm able to identify which part of the system has led to this type of problem. And the other challenge comes like similar failure modes can be generated to the different system and the different parts of the same system. So you get the false alerts and false alarms also. So the sensors or the monitoring system that you use, they have their own shortcomings. They are normally below 4% to 5% for a, it's a quite industry. In the industry, they accept it up to 4% or below 4%. Yeah, so when we have done the development, done the product test, trial, you start the launch or operation of the product. Irrespective of whatever you have done, there is always chance that your stress has somehow overlapped the strength of the product and the failure likely to happen. So in the industrial side, people, when they have done the launch the product and started the operation, the team who has been working on the product moves away to the new product, new system, or new process. But recently there has been quite a lot of discussion in the commercial side that even if the project has finished, you have delivered the product, a certain core skill set should be kept in the same project in the operational side. And what we do when you launch the product, you bring back all failures, all returns, all points of concern that system has generated for thorough analysis. And normally when you bring it back, you'll find it around 20% had the genuine reason that why system has failed. And 80% is more on the human reliability side, because we are quite weak in modeling the human behavior, how they will use the system. It can be either due to lack of training, lack of understanding, or in the design itself, you have not thought about those various use conditions. So my recommendation is to do thorough analysis in the beginning for any concern that is raised during the starting phase of the operation or launch of the product, and then act immediately on those root causes and implement the preventive actions for those root causes. So, and in that way, keep on improving the product. Challenges becomes, as I mentioned earlier, the resources. When you move from one product, you do the design, launch the product, it starts to work, and then you move the core skills in another area. That's where the negotiation happens between different teams, different management. And then another question comes like, when do you stop this activity? See, it's again, do you see the risk or do you see the opportunity in improving these failures or removing those failures? And then other aspects happens like when the product has been in operation for some time, for some period of time. How do you measure those performance? So in the beginning, if it is a mass production, or if it is a quite high number of products that is going to be used from the beginning, the batch failure rate has been very useful to indicate the quality or reliability of that product that is going out in the field. And that batch, by the batch, I mean either you can look into the production month or production country, or if you made any change in the product. So homogeneous, is it the homogeneous population or not? That information is lost many times when you're doing the data analysis. So I prefer to any product that you are going to use in daily life or in your system or going to monitor it, we should be able to identify from the failure data itself that does it belong to the specific week of production, a specific week when it was produced, when it was sold, when it was put into operations. And then on the longer term, field failure rate, that in many companies, it's still a big incentive for the business. In Nokia, out of 5 performance metrics, like field failure rate was one of those. In a Sky Broadcasting, that's also like incentive of the executives and all the employee depends on the failure rate, how often it has failed, and that is measured every year. And normally you monitor continuously. The challenge with the problem with the field failure rate is that it doesn't say about the product reliability at all. It gives some indication that what my warranty population is doing, or the product that I have collected the data, how it is doing in the field. It doesn't say how my design has been with the product. So that just to understand the difference between the batch failure rate and field failure rate, I just give an example. Like if you are going from point A to point B, which is 100 kilometer further, and if you're driving in 100 kilometer speed per hour, you will be reached within 1 hour. But your speed at the time of 20 minutes will not be 100 kilometer. You may be driving at a 20 kilometer or maybe driving with the 70 kilometer. So this batch failure rate responds to that at that specific time, what is the status of this product, and then you can adjust your speed accordingly to come up to 100 kilometer per hour average speed. Then when it comes to the measuring the failure rate, I have seen in commercial industry there are around 10 to 12 different way you measure the failure rates of the product. Some industry, they say, okay, 10 failure out of 100, 10% is the failure rate. Some industry say, okay, 10 out of 100, if all failed in only December, so it is not 10%, they calculate a different way. Then they get into, some industry have better information that I had sold only 2 units in January, or I put operation in March in so many units. So you look into the different levels of details and you can come out different values of the failure rate for the same product. And that becomes a challenge because when from the supplier side, you are agreeing a certain reliability for a product. And then from the user side, if you don't, both of us has not agreed that how will we measure it? It comes a lot of conflict, and we had to go to the court also for coming to the final conclusion. So this can be very sensitive. So it's always good to, from the requirement stage itself, get into how are we going to measure the performance if we are putting the performance as a criteria in the supplier side. And another challenge becomes the noise in the performance data. So if you give the data to somebody, you come at a failure rate, but when you start to know the story behind those data, you come to the very different failure rate calculations. So one should be very careful and must be aware of the background of the data. Then the last stage during the operations, your investigation side, and you make changes in the product, in the system, or in the process to improve it, and feedback to any new product that you are creating in the which is in the development phase or negotiating some other products or systems. And this, irrespective whether it is defense industry, telecom industry, or in electronics industry, this is the weakest point in the sense that whenever you are doing a new product, you will see they'll be repeating the same mistakes many times. We had, like in Nokia, we had some components, or in a satellite receiver side, some components has been failing all the time, and it still fails all the time till someone really takes into account that a thorough reliability investigation is done and a thorough change is, a managed change is implemented in the business side. Otherwise, human beings are very tend to have this inertia that this is the way we have done the design and it has been working for the last 5-10 years, and they keep on doing the same way. So as a reliability person, you have to do a lot of negotiations, facilitation, and managing different aspects of a product. So this is the famous our PDCA cycle, where you performance is happening, you monitor it, you improve it, you plan it, then you plan that what you are going to do, and then you perform your analysis, then you monitor that is it working, and then you improve it, and then you keep on going. So this should continuously go on, and this feedback is the most critical item for making any system highly reliable, whatever is a railway system or defense system or any system. The challenges is in any industry, I have not seen yet a very good feedback loop. Like there is no department or no single point of person who coordinates all this feedback loop at the same time have a technical understanding to implement those changes. It happens piecemeal wise, and also the priorities and incentives drives this feedback loop also. Like what is the priority in the business or in the industry? Is it creating a new product, making very shiny good products, creating a new technology, or is it improving the previous ones? And then incentives, how these are incentivize those people. So coming back from the, this is my last slide. So starting from the beginning, you start with the reliability requirements, and it is not just one event at one point of time that continues throughout the product development, but you initiate, your priority should be to start with the requirement side, and that may continue even when your product is during the operations, because you will learn a lot during that process, and that will feed back to your reliability requirement for any system, PHM or RAMS system you're trying to analyze or trying to develop for any product. And then your reliability prediction also depends, either you can do the standard based or you can use the batch failure rate or field failure rate site analysis. And then sometimes in the requirement and prediction, even if you use the learnings to improve your requirements attributes and your prediction methodology and your demonstration methodology, and then you all feed back into your design for reliability side. So it's all continuous process, and we need to have a systematic approach to the reliability. One has to look into from end to end point of view. Like it is not just at one point you can just close the reliability side. And then other thing that I find very important that it's a cross-functional. It's not just the reliability person who is responsible for the reliability. It's everyone involved in developing the product. Like in marketing side, when I was looking at the Sanofi medical devices, like what should be the reliability of those. So I had to get in touch with the marketing side, repair side, logistics side, like how much many returns we can accept, what is our facility, reverse logistic facility that we can collect from the field, those equipment, how can we, to meet the regulatory requirement that we will have only 99.5% failure of this product. So there are a lot of financial side, business organizations, different disciplines involved to achieve the success in your RAMS program or reliability. And then ultimately it's the mindset. Are you looking at as a risk or looking at it as an opportunity? Once you look at the as an opportunity, then you get tremendous support to do very extensive reliability analysis and you make the product reliable. So in summary, for reliability assurance, start from the requirement, go to the prediction, do the design for reliability. When the product is launched, please do continue with the feedback loop. Thank you very much.
Thank you very much, sir, for your talk. It was very interesting, sir. And we are really very thankful for you to sparing out your time and you are here with us. Thank you so much, sir.
Thank you.
Now, the next speaker is Dr. Mukul Verma, sir. He is the RAM consultant at Gurugram. And he's going to cover the RAM safety, which is again railway safety, which is very important aspect. Dr. Mukul Verma has extensive experience in academic and work experience in the fields of RAMS and design of safety signaling systems. He has got a doctorate degree on design and development of safety critical systems from Indian Institute of Technology, Delhi. He is a former railway signal engineer and now working in the area of RAMS. Dr. Verma is a chartered engineer of Engineering Council UK and IETE India and fellow of IET UK, IRSE UK and IETE India. He is also a certified software quality professional. I just want to add one more thing, that he is also part of our joint consultative committee of rapid alternative energy and mobility. And he is one of the persons who has been maneuvering this boat of RAIM and our center and guiding us from time to time. Thank you very much, sir, for being here. Sir, we'll be eager to listen to your talk also. Thank you, sir.
Thank you, Dr. Vidushi. Ladies and gentlemen, I will be talking about something about important points for regarding railway safety. So let me share my presentation. Screen. Yeah, can you see my slide?
No, sir, right now we cannot see.
I have already shared it.
Yes, you've just shared it. Thank you so much. Now we can hear you as well and see your slide. Thank you, sir.
Okay.
Yes, sir, fine.
Okay, fine. Thank you very much. I will be talking about some important issues on railway safety. First thing is about history of railway safety. History of railways is about 2 centuries old, and so is the history of accidents. The picture you are seeing on your screen is about the inaugural run of intercity trains between Manchester and Liverpool on 15 September 1830. This was the first train in the world which ran between 2 cities, and it met with an accident. So accidents are part of all modes of transport. Our endeavor is always to minimize the risk. What is risk? We will see. Risk is a combination of severity of an accident and probability of accident. So we will see some important issues on safety. That is, first thing is, what is safety? We will try to define safety. Can we quantify safety? Well, why do we need to quantify it? Unless we quantify, we don't know where we are and where we have to go. Have we improved? So to measure all these things, it is important to measure safety. As Dr. Chaturvedi in the previous session said, we have to quantify quality. Similarly, safety has been quantified, and we will later on see that it has been quantified into 4 levels universally for all modes of transports, whether it is road vehicle, whether it is aerospace, or whether it is railways. This is safety integrity level 1, 2, 3, 4. And the level of safety is decided based on the severity of consequence of accident. Next question is, can we achieve 100% safety? Well, answer is no. There is some accepted level of risk which has to be taken by depending on the society. Every society, every country has its own minimum accepted level of risk, and safety is only an insurance that you will not have more than the small amount of risk that you have already accepted. Well, if 100% safety is not possible, then how we can determine what is the amount of safety we need for a function? For example, in the railways, there are different functions like signal clearance, giving command to the interlocking system, and so on. For this, our safety standard CENELEC provides a guidelines to decide what level of safety is required for what level or which function. We will see about CENELEC later. Then, having determined the safety level, how do we go about achieving it? In other words, how do we design different subsystems and operating procedures to be put in to achieve the required level of safety? Again, CENELEC comes to rescue, and CENELEC is the universally accepted, well, not universally, but at least in India and Europe, CENELEC is the Bible for railway safety. So CENELEC gives the guidelines to decide how to achieve a given safety level. And having achieved the safety level, we have to show to the customer or to the public in large that we have achieved this safety level. So CENELEC provides the guidelines how to achieve and how to demonstrate the safety level. So issue number 1, we will see what is safety. Safety has been defined in CENELEC in just a few words: freedom from unacceptable risk related to human or environment. Now, there is a key word here. This is unacceptable. That means, as we discussed earlier, some amount of risk has already been accepted by the society. And when we talk of safety, we only make sure that we don't increase the risk beyond what is already accepted by the society. And we have seen earlier that risk is the combined effect of severity of hazard or accident and probability of the hazard. Well, hazard is a technical term. Hazard is a situation where there is a possibility of an accident. So let's say in plain words that risk is the combined effect of severity of an accident and probability of an accident. If the severity is very huge, then we have to reduce the probability of that accident to the acceptable level. We have talked about CENELEC. Here, I would like to spend a few minutes on CENELEC because this is very important for the railway engineers. CENELEC has got 4 standards. The first is EN 50126. This is for railway applications. This is for complete railway domain, whether it is signaling, whether it is rolling stock or track. 50126 applies to the complete railway application. It has got part 1, which defines the RAMS process. So this is not only for safety, this is for reliability, availability, maintainability, and safety. And part 2 deals with particularly with safety. So these two parts, they are applicable to the complete railway domain. Then there is another standard, that is 50126 part 3, which is a guide to the application of 50126 to rolling stock RAMS. This applies only to the rolling stock domains. Apart from this, there are 3 standards which apply to signaling systems. 50129 particularly provides the guidance for electronics hardware as well as the system. I have seen 50129 being applied to rolling stock also. So people have started using this for rolling stock also. Then next standard is 50128, which is again for signaling system, but for software for signaling system. And the last one is 50159, again for signaling system, but for safety related communication. As you will be aware that metro trains, they run mostly on Wi-Fi and maybe on Tetra also at some places. But the communication system as it is cannot be used to control the safety functions. So a safety layer is built up over and above the communication packets, and how these safety layers are to be put, that is described in 50159. Then we come to the acceptable level of risk. We have talked that every society has got its own acceptable level of risk. It has decided, and the risk should not be higher than this acceptable level. There are various methods for various countries they have applied. Generally, the most popular one is as low as reasonably practicable, LARP method. This is a very popular method, and in India also we are following this method. We will see how this method is applied. Here also kindly see the key word, that is reasonably practicable. Again, the risk is not to be reduced to 0. We need to reduce it to the reasonably practicable level, which is acceptable to the general public. Next issue is safety quantification. I mentioned that safety has been quantified into 4 levels. These are level 1, 2, 3, 4, highest being the level 4. So for any hazard or any accident, we look at what is the severity of most possible severity of the accident. Maybe head-on collision. For example, suppose there is a hazard in which conflicting signals have been cleared for 2 trains. There may be head-on collision, there may be side collision, or there may not be any collision at all if there is no train. So we look at the highest possible severity, and that is head-on collision. Since this cannot be accepted, its probability has to be brought down to a very low level, and that is given in the Senelec as less than 10 to the power minus 8 per hour, which is about 1 in 10,000 years. So similarly, for other things, for example, doors of a metro train open in the moving train is a is not a good thing. I mean, it is not acceptable, but it is not as severe. The consequence is not as severe as the other one. Probably this is assigned a safety level number 3 or 2. This is a subjective matter, and the probability of its occurrence is reduced to less than 10 to the power minus 7 or minus 6, and so on. This way, for every function of the railway, we assign a safety level, and then we reduce the probability to the prescribed level. Apart from this quantitative probability, Senelec also suggests, or not suggests, it requires, mandates certain qualitative measures to be taken. For example, for highest level of safety, SIL 4, it gives for any software which is controlling a SIL 4 function should not use online memory allocation, or should not use nested pointers, and so on. So there are similarly, there are for hardware also, there are certain guidelines available. Well, issue 3 we discussed was, is 100% safety possible? This has already been answered. No, 100% safety is not possible. Some minimum amount of risk that has already been accepted, and we can bring down the risk to that much amount. The next issue is, how can we determine the minimum level of safety required? Well, we have seen some methods of determining the minimum level of safety, and one of them was LR that we have already seen, which can be applied for determining the safety level. Now we come to how to achieve the required level of safety. Again, Senelec has got such guidelines. If you follow those guidelines, you will achieve safety integrity level. For example, for products, it has given a quantitative requirement, which we saw for SIL 4, it was 10 to the power minus 8 per hour. We have to bring the probability of such failures to less than this. And there are some qualitative requirements. An example of metro rail, the safety is allocated to different subsystems, for example, signaling, rolling stock, etc. And each subsystem is required to demonstrate that the required safety level has been achieved. Then the last issue was, how do we demonstrate that the required safety level has been achieved? Well, all documents have to be prepared. You have to give a justification. You have to calculate and show that you have achieved this probability of failure has been reduced to 10 to the power minus 8 per hour for SIL 4, and maybe minus 10 to the power minus 7 for SIL 3, and so on. Documentary proof for quantitative requirements as well as for qualitative requirements, that you have followed all the guidelines, that, for example, safety audit has been performed, that your design engineers are well qualified, etc. Giving all these things, a safety case is prepared and put up to a independent safety assessor who assesses everything and then certifies the system to be safe at the required level. So these are all the 6 issues which I wanted to touch upon. And concluding my lecture, I would like to say that we have that Senelec is the Bible which guides us in determining what is the minimum safety level is required, how these levels are to be achieved, and how do we justify that this safety level has been achieved. And the level is normally decided or determined by methods like LR. Thank you.
Thank you very much, sir. So we got some insights on safety also, and we look forward for more of your presentations in future, sir. Thank you so much.
Thank
Now,
you.
with us, Dr. Anirudh Gautam, sir, who is Executive Director, Research Design and Standard Organization, RDSO, Lucknow. Dr. Gautam is a mechanical electrical engineer from prestigious SCRA scheme of Indian Railways. He has served initial years maintenance of carriage and wagon, maintenance and operations of steam locomotives, operation maintenance of diesel locomotives, and train and crew management in the challenging eastern sector of Indian Railways. He has worked in the area of manufacture of diesel locomotives at Diesel Locomotive Works, Varanasi, and then he moved into a niche area of design and production. He is credited
Thank you.
road feature on an export locomotive and was instrumental in building the first indigenous EMD design locomotive in India. He has developed Alto locomotive electric fuel injection system, which has been commercially successful. A mobile anything test car, which has been used for measuring level for locomotives in India. The main area of interest are energy production devices, fuel cells, hybrid powertrains, and sustainable motive power systems, control system development, and structure optimization. His other area of specialization is reliability and has been for railways and conversion of energy to operate on methanol. He's working
Okay.
his hybrid trains and the future of railway traction also. And he holds his master's in quality management from BITS Pilani, a master's in engineering in engine systems from University of Wisconsin-Madison, USA, and PhD in renewable energy engines from IIT Kanpur. Sir.
Thank you, Vidushi. Am I audible?
Yes, sir, you are very much audible. The presentation is there on the screen.
Okay.
For us.
Okay, so since we are running short of time, I will be a little quick on my presentation because we have a question answer session also after that. So I'm going to talk about RAMS and PHM on Indian Railways specifically. The present status is that Indian Railways is very seriously into RAMS and PHM. RDSO has set up where I work. It is called Research Design and Standards Organization. It is the research and design wing of Ministry of Railways. Presently headed by our Director General, Shri Virendra Kumar. So RDSO has set up a Center for Reliability and Integrated Systems Engineering. And this center is equipped with a central server, reliability software, and dedicated internet connectivity. And we have trained certain personnel from carriage, wagon, electric locomotive power departments. And we have taken up certain projects in collaboration with IIT Kharagpur from the group of Subir Chaudhary School of Reliability and Quality. For example, we have taken up RAMS analysis of LHB and ISCF coaches, FMECA of coach bogies, RAMS analysis of diesel locomotives, reliability study of the traction motors of electric locomotives, then data collection system in coaching depots and railway workshops, reliability analysis of turbochargers of diesel locomotives, and some of the projects. One of the things that has come to our notice, that data collection is an area of immense improvement on railways, and we are working towards improving it. For the IIT Kharagpur projects, I would like to mention that I have worked with Professor Goel, who works with Professor Chaturvedi. Recently, then Ministry of Railways started looking at implementation of the RAMS and the PHM program on a very wide scale all over Indian Railways. And recently, Railway Board has sanctioned a project for implementation of EN 50126 RAMS for rolling stock of Indian Railways at a cost of rupees 400 crore. And so EN 50126 has already been spoken by Dr. Verma, so I'll not repeat that. And it is the purport of the project, this project which has been sanctioned by the Railway Board, to cover all aspects of life cycle of rolling stock, that is design, manufacturing. So design begins at RDSO or at production units, manufacturing, production units, ICF, RCF, and MCF, railway workshops, then also private workshops, the wagon manufacturers, maintenance depots, and maintenance yards. And we have actually prepared a concept note, and we are in the eventually this implementation will also be rolled out for all assets of Indian Railways, that is track, signals, electric infrastructure, etc. The vision of RDSO is to be a leader in research and innovation with focus on reliability and maintenance of railway systems. So that fits in beautifully with our RAMS and PHM initiatives or Ministry of Railways. Certain PHM initiatives have already been taken on Indian Railways. For example, condition monitoring of permanent way. We have these track recording cars and oscillation measurement cars, where we measure the unevenness, alignment, twist, gauge, vertical wear, lateral wear, angular wear of the tracks, and also look at the various physical conditions of the sleepers, track fittings, etc. And we are also doing subjective assessment of track health through acceleration monitoring at the bogie pivot and riding comfort. And we are also planning to do track components scanning through high resolution and high speed cameras to identify the track defect, component defects. Then we, in the field of traction installation, that is basically the overhead installations, we have got tower cars equipped with measuring and recording instrumentation. We also plan to measure OHE geometry parameters, span-to contact wire interaction. Then locations with imminent failures can be attended in time and we are planning a predictive monitoring of insulators using ultrasonic scanning, thermal imaging and partial discharge. And RDSO has also prepared a draft guidelines for condition monitoring of transformers. Then on the coaching side, we have developed the onboard condition monitoring of bearings of coaches. We have used in industry, one of the private industries, wireless condition monitoring system for condition monitoring of wheel bearing and track as part of a pilot project. And we are also using sensorized bearing with tread brake unit with the speed and temperature sensors. Then in the signaling, we are using the Senelec standards, which Dr. Verma already talked about. And we are looking at SIL levels and data loggers. Railway signaling system is using a lot of data loggers, which have been networked, and in which 3 types of alarms are generated: maintenance, safety, and traffic related, and sent in SMS to maintenance staff to reduce equipment downtime. On the locomotives, we have developed remote monitoring and management of locomotives and trains, that is RAMLOT, which gives an online monitoring of the loco health and fleet management through web-based application. We are also doing wayside monitoring of bearings through acoustic signatures. Bridge condition monitoring projects are also being undertaken. We have already taken some projects in which we are using underwater drones to study the piers of the bridges and to inform the and to give out the data on the condition by taking photographs and also assess certain other attributes of the piers and the structures. Electric locomotive components online condition monitoring is also being done. So this is as far as the PHM on the Indian Railways is being done, and there are certain other pilot projects which are also being done. But there are certain issues for PHM on Indian Railways. Most of these systems are standalone industry developed systems being used. There's no common protocol. So we very urgently require a common IT backbone, and Indian Railways, Ministry of Railways is working towards that. Of course, we have not covered all the areas, and we would like to cover, make it as a system of systems. And we would like to use data analytics, AI, ML based RUL, remaining useful life predictions. These are not available right now, but we are trying to work in that direction. At Shakur Basti, we have set up a PHM center. That has started working, but it needs to be augmented quite a lot. And we are doing more experiments also in certain other areas, like traction motor, bearing temperature, and transformer condition monitoring, etc. However, we are also looking at a common program for adoption of a structured PHM which should be done by Indian Railways. And the most important thing is that we need to skill our Indian Railways personnel in PHM and data analytics very urgently. So this is we have made a RAMS for rolling stock of Indian Railways. A quick, we will start right from the purchase order, manufacturing data, workshops, depot yards, then onboard diagnostics, wayside diagnostics, and customer requirements. And Chris is our organization who handles our IT and data related work. So Chris will be hosting all these servers. The RAM servers will be hosted by RDSO, and then we'll be doing the various activities like faulty analysis, reliability centered maintenance programs, DFMM, then DFR, design for manufacturing and maintainability, reliability, operations, lifecycle costing, FMECA, and all this will be all be integrated in design, manufacturing, maintenance, and operations. And of course, then we'll have the dashboards for various, starting from the minister, right down to tracking the assets and their problems. This is the framework for RAM LCC management, which I have taken from the book of Professor Derson. And this basically shows the various concepts of RAM LCC management. There is concept and definition, design and development, manufacturing and construction, assembly and integration, operation, maintenance, and disposal. And then at various stages, we have integration of RAM LLC requirements, then determination of requirements, and demonstration of requirements. And on the feedback loop, we have the maintenance engineering, maintenance and apportionment of RAMs and LCC requirements to subsystems. So this is a framework that we are trying to follow on Indian Railways as well. We have got on the Indian Railways, we have a huge inventory of assets. We have 3 lakh wagons, and that is 300,000 wagons, 60,000 passenger coaches, 10,000 EMUs and demos, 11,000 locomotives, 70,000 kilometers of track, which is increasing every day, 50,000 kilometers of OFC lines, 7,500 railway stations, 33,000 kilometers of track circuiting, 45,000 kilometers of electrified lines, 1.5 lakh bridges. So asset management and RAMs of assets becomes a complex due to linear nature of these assets, because they are distributed all over the country and they are moving all over the country, for example, the rolling stock. So it becomes a little more, a bigger problem for Indian Railways because of the size and the volume. So for the rolling stock, coming to the rolling stock, the design is done at RDSO, vendor premises, and at the production units. Manufacturing is done in 3 factories. And then we have a large network of maintenance points for both coaching and wagon stock. For the coaching stock, we have workshops, primary depots, secondary depots. For freight stock, we have POH and ROH workshops, maintenance yards. And then we have preventive maintenance schedules, trip, quarterly, 6 monthly, yearly, 2 yearly, followed by POH. So that's a typographical POH. 44 railway workshops on Indian Railways in different geographical areas to carry out these activities. So you can see the lot of money we are spending on maintenance activities and in asset and in ensuring that the assets are available and they are safe to use for the passengers. We would like to bring down those costs at the same time maintaining the safety of these assets. These are the preventive maintenance schedules we have got 2 types of coaches, LHV coaches and ICF coaches. And then we have wagons. So we have got different types of maintenance schedules. For the concept for the roadmap that we are going to do for the RAMS and PHM for our rolling stock, we will implement EN 50126. So that will include our Center for Reliability at RDSO, CRIS, production units, workshops, suppliers, maintenance depots, maintenance yards, and private wagon manufacturers. We'll be requiring a host of machines and equipment, including data analytics, AI and reliability engineering related, integrated maintenance units and diagnostics and prognostics, then direct part marking for the traceability of the various components, smart methodology systems, then learning management systems for our scaling of our people, machine capability study processes and their equipment, smart material handling systems. In the business process engineering, we'll require vendor development process to be rewritten, procurement processes to be rewritten, introduction of 16SA vendor development procedure, which is a standard, international standard, maybe use of ISO TS 16949 and QS 9000, stores and finance code revision, then production process reengineering, use of modularity in design and production. This is the intelligent manufacturing system we are looking at in our production units so that we can improve the RAMS characteristics of our assets. And this is a brief about modular manufacturing, which I'll not go into detail because of the shortage of time. But I'll just like to mention here that in modular manufacturing, there is a requirement of a digital twin for the complete production process, and in the digital design modularity, it is called a Lego design, wherein the designs are standard of the component parts of the components. The designs are standard that can be put together either to make a house or an aeroplane or a scooter. So that is the new concept of manufacturing which is coming, which is basically designed for high reliability and manufacturing. We also have introduced Industry 4.0. MCF has started the process of implementing Industry 4.0. That will also add to our increasing the RAMS reliability of our assets. To start with the coaching assets. And then we are looking at various methods like a digital backbone for collection and maintenance of design, manufacturing, maintenance, and operation data, connectivity between CRIS, RDSO, production units, workshops, maintenance sheds, then implementation of RAMS management system for rolling stock, and capability index, process reengineering, and using various methods. We are also looking at skilling and knowledge enhancement. Certification courses and RAMS and PHM that we have tied up with the Gautam Buddha University, and 2-year online master's courses in RAMS and PHM, webinars, workshops and fields, hands-on training sessions, PHM and RAMS training to become part of our central training institutes. We are looking at handling and logistics, so smart material handling, material movement corridors, including underground and overground material tracking systems with digital identification bins, scaling in material handling. And these are the timelines that we are looking at 2 years' time. It is an ambitious target. However, we are very firm and resolute in our desire to do so. And these are the various milestones that we have provided on this timeline. So we plan to finish this project in next 2 years' time, and also take up projects in other areas like infrastructure areas for implementation of EN 50126. So basically what I'm trying to say is that Indian Railways have recognized this problem, and they have taken up this challenge of introducing EN 50126 for its assets, and also implementation of ISO 55000 for asset management. We are willing to partner with the industry, with academia in these programs, and I welcome all from industry and academia to participate in this. We'll be sharing our contact details shortly. Thank you.
Thank you very much, sir. Your kind support will be always required to start up this certification course, and we really look forward that we come up with such a certification course for all our participants, those who are interested in RAMS and PHM programs. And we are soon going to start the MTech programs also. And I have been receiving a lot of queries on that. So now we are open for the queries. Some of the questions have been shared on the chat window. So people who want to just ask questions, they can raise and they can, we can take up the questions. Those questions there are certain questions which are in the chat window also, if the speakers will like to address some of them. Like how is the SIL level of any item, for example, is selected, or SIL 4 while PSD system is in SIL 2, SIL 2.
Dr. Vidushi, actually my computer shut down in between, so I don't have all the chat messages. When I reopen, I get only 5 or 10. So if you want some answer from me, why don't you read out the question? I will give my comments.
How to select the SIL level of any item, for example, PSD door relay in SIL 4, while PSD system is SIL 2. Jayant Pandey sir has tried to address this question, answer this question by saying that decided on the basis of the risk THR being accepted from the function performed by a unit. So if you want to throw some light on this, sir.
Yeah, as I already said, the SIL level or safety integrity level is decided by the risk that is involved. That is, what is the severity of a hazard? If door opening may create a hazard for, say, catastrophic, there are 4 or 5 categories: catastrophic, then very serious, major, then minor. So it depends on what kind of severity you attach to it, and it is a very subjective matter. This has to be discussed in a workshop involving all the stakeholders of the metro. And practically, I have seen that door opening, if you take the example, it is assigned level 2 or 3, whereas other signaling functions which can create catastrophic consequence, like I gave the example of 2 conflicting signals being cleared for 2 trains on the same line. This is definitely SIL 4. So this is a subjective matter, and you have to decide which is less, which severity is less, how much less.
Thank you, sir. Any other participant want to discuss anything? They are open for the question. They can unmute your mic and you can ask the question. We will be sharing the email IDs of the speakers also. In fact, a lot of question has been answered in the chat window itself. And I'm very thankful to Jayant Pandey, sir. He was a part of our joint consultative committee meeting also, and a roundtable meet. So, and he has given a lot of insights for our projects. So finally, we have come to the end of our webinar. I want to thank all the participants, though there were some technical flaws which happened during the YouTube transmission, but then we were able to make it up. I have the recordings of all the speakers. So after their consent, we'll be sharing it to you and the presentations. So those who are interested in watching those presentations and those recorded sessions, they can always go through them. And I really thank you. Before I conclude this whole session, I also want to invite our chair, Rain. Sanjay Sharma, sir, to give a final word.
Okay. Am I audible?
Yes, sir.
Okay.
Yes.
It's been really a great success, I think, because all the speakers have given a lot of insights in their fields. I'm extremely thankful to all of them, and same time thankful to all those persons, all those delegates who has participated in such a presently this whole world is passing through a situation of pandemic COVID-19, and I think before to end the program, let us have the Mangal Mantra. Let us pray God, Almighty God, for this nation and this whole universe. And I'm starting with this chant mantra, Shanti mantra. That is, Sarve bhavantu sukhinah, Sarve santu niramaya, Sarve bhadrani pashyantu, Ma kaschid dukh bhag bhavet. Om Shanti, Shanti, Shanti. Namaskar.
Thank you very much, sir. I also want to thank my technical team who has been on their toes. Dr. Neeta Singh, Dr. Sandeep Rana, Ms. Neeti, Ms. Gamini, who has been working throughout their, the time working and maintaining the whole show. And thank you all the participants, and thank you so much all the speakers. Thank you very much, sir. I'm very grateful to you that you have given us time to be over here. Thank you so much. Namaskar.
Thank you, Vidushi, and everyone.
Thank you, sir.
Thank you, Vidushi. Thank you.
Hello. Oh, sorry, my mic was mute. Dr. Vidushi, I have a question. Will the presentation be available for everybody? Will you be sending by mail or somewhere it will be available?
Sir, I'll be putting it in a. I'll be sharing this presentation on a link, and we will share that link.
Okay.
And after the permission of the speakers, I'll share the videos.
Okay. So this link will be to the PowerPoint slides that has been presented, is it?
Yes, sir.
Okay. Okay. Thank you.
Anything else?
All the participants, Google Meet.
Vidushi, I would